宋伟他讲他要我们才按对吗？还是你直接放弃？
我直接，because 你看我已经这么多事了，那就全部人等，然后他呢，这个哦，你才可能看得到哦，现在是这样。
哦，是我可以 stop 的啦，我 stop 了，如果我要再 start 的话，已经整个不是这样。
不算了吧？
哎，没有没有没，
你可以说
live stream 吗？
哪一个？
看看你等一下。
哦，他不会再问你了啦。OK，这样说，昨天他们就是这样，不要 log out，一 log out 就完蛋了。
对。
啊，他记住了啊。这样说，你其他的你还可以吗？还记得吗？刚才我们课的时候，他根本没有出现这样。
对。哦，我要 download 在其他电脑我才可以这样做。
对。
所以我要你 log 进去。电脑，你的谷歌，你的雅虎，因为他没有 send 我那个 email，我还没有 send 我们这个，他只是 screenshot 给我。
你 send 给自己啊？
他 screenshot 的，他用 screenshot 给我们。
对，可以 send email 给自己吗？
没，他只是 send 我们这样的耶。
等一下，
这是 screenshot 来的，他不是 send by email 还是什么？
没有，他 screenshot 没有 screenshot 到一半那个
没有，他是给我的。
他 screenshot 了，他 screenshot 错了。等一下，
可能是在 Dropbox 里面有。今天的什么？是 underside 吗？还是什么？对，这个是几时 send 给你的？刚刚的呀。
忘记了。他刚才 send 的 screenshot，
他是 send 那个 screenshot 给我们。
是傻了。
哎，为什么你会有这个？
之前已经有的，从哪里有的不清楚。说问题，我这个是插在，我没有弯度去，我不懂哪一个是哪一个了。所以你要 figure out。
PG 83。
这个是没聊过。
没有，NUS。
没有啦，NUS。because 我们现在 log in 了吗？你一按你的 NUS 没有哦，
哦，等我换我自己
就变成那个
补强。
你看我现在也是用我的。
我是那个。
啊。
OK。哎，对对。
对。
我靠，当时scan 确实强。
哎，麦 OK 嘞？
弄的是哪一个？
诶，
你不对，我
要按开始 hold 嘞？
我后啦，
有咩？
我跟他比，
啊，
我看了没去，
哦呀，看我看到那个白去丢的，
白面没
竟然是。
真是白面我进去改，还有那种还在的，
你看啊，once 我们 because 首先 log out，现在我们一 stop 了哦，我们一进去就可以就不用 key 了。
啊什么？谁？再讲就是
live，我们刚才已经 login 一次了，然后我们
没有，我有一个 minute 的，我昨天 test 的时候，我昨天在阿妈楼上，我下来，我是这样 click，他就直接进去这样子。
啊，因为我们 log out 了，所以要再把你多一次。所以
他那边没有，他还是一样，还是 stay 在那边的，我的 setting 没不见的。
我的你看，你刚才看到吗？SR1 SR3，
我外面的我的号，在顶底面都还在的。人民全部都要晒对是吧？
对，
走吧。反正 AB 也没有人来，A 也没有人来，大家自己，哼。
这个麦搞定了吗？
哎呀，对。
收这个哦，你现在关掉对吗？
给到他两寸，他跑了。对啊，上了就不要管他了啊，就这样啊。
对，我们上那个 Zoom 不是要 key 这个的咩？那个 Zoom link 不是要 key 这个进去的咩？因为你刚才是放 new 吗？但你没有 key 这个。
New listing ID。
你完全没有 key 到啊，你只是按 new 而已嘛，不是啊，完了。说白了应该是都 key
这个是否别人进来 join 的？比方说，这个就是这个的。
你要看他的号码是什么？不是嘞，833嘞，那个是880呀。
I see。
你懂我讲吗
？Join
你
meeting。
应该不是 join meeting 吗？啊，你应该是 join 那个什么东西，不应该是 new meeting。
一下啊，这个是否 SR
这个之前的
可以注意对 mistake。
这个可以看掉了。
stop。
过去，哎，你看弄了一次就可以了，哎。
不要录了啦。
啊
录了。
啊，
你在啊？我这里不去这种。
哇，这个 camera 比刚才的还猛，这个的比刚才的还猛。
还猛啊！我还以为刚才还好一点。
你等我去，我们去那之后，你爸爸给他上了。啊， There's test.
你在国内吗？
我现在在国内，我刚从上海过来，
你是
啥都回来了。这段时间其实主要在忙申请。前段时间跟那个水源这边的工作有一些follow up，做。
Let's see.
Me?
Yeah.
I'm a student volunteer. Are you speakers?
No, I'm the holiday.
Oh, you're the organizer, right? Okay. Cool. Yeah. So I've got a list of talks here. The first one. Which one? Oh, the first one. Right. Okay. I see. Yeah. So that, and that's at 9, and that's not being recorded. But then the other one is all.
Oh, right. He knows not. Oh yeah, you requested.
Yeah. Okay. Right. So that's this one. Then everything else, there's one like remote one, and that's actually just after. So
I should just see.
yeah, seems to be. So I'll have to pause the recording and things.
我也不知道，因为我自己没有明确的 offer，先圈的。
你想去的。
是。
Wonderful.
Yeah, you're going to be a second chair.
Get ready. Good job with that session, Chair.
Nice. I was wrong.
Thanks for organizing.
Yeah. Actually, the one to one did the everything. Not count.
Oh, gosh. Yeah.
So I'm doing that.
Great. Then like we don't have to like do stuff about substitution. Yeah. And that was such sort of that's something that it should yeah, because the quote right. It's also your making sure you don't need a vending staples or a tape variables or a contour variable. You have a chunk of the contour. And now you got more bound variables. Can handle that.
Meta programming process. That's a bunch. Yes. Oh no, I just saw her like wandering around like near the website. Yes. Oh, that's nice. I feel like it's the wrong approach to solve. Like I think the answer to have is like I think we want more language like this, not less. I would something where it's like, oh, and then you have to like annotate explicitly like your like binding structure of your language, and it's like extract something. It's like the fact that it's really generic, like really. For things that are less language, but I think you really visual language you could be like less. Yeah. Yeah, I agree. This feels like a thing, like general programming in like Actus. Right. You want to like do functional programming in Actus.
But yeah, I mean, there is like,
yeah.
Like the underlying units are going to be different. It may be better to pick like an older approximate.
Yeah.
But then yeah, structure feels different. I will.
Yeah. Yeah, that was I know what a sigma is. It's a monoidal.
I got blasted by the
I came across this paper over the summer. Not like no, I was just like on the weekend, I was getting distracted by like trying to understand like second order abstracts. I went down a rabbit hole that started with like SOGATs, and then I just tried to understand like just following links. And I got to this paper. I got really confused. I still don't understand it at all. Yeah, I was entirely lost. Yeah. Yeah, sorry, the word calling calculus. This is like a set of equations you can do to like do a bunch of computations.
Yeah.
Right. Is there like a similar set of like computational reasons? Like, I don't know. Donata and stuff. Is there like the Donata lemma calculus, and I just like can just like start using the sign a bunch of times?
Yeah, so I mean, yeah.
Yeah.
There's this thing you can do.
Yeah.
Yeah. Also, the unit limit has a formulation. It's a coend because
Yeah.
You get like a gold square. It doesn't really look like. Or just like. Plain calculus.
Yeah.
Principle.
Yeah. Because I'm just thinking, like, there's definitely a lot of, like, there are some proofs that I've read, like, writing, where it's like, oh, and I have some things, and then I like apply Oneta, and I then a bunch of equalities, and I apply Oneta again, and it's like, it would be nice if like all of these, if there was just like a giant like table, like every equation, and then it's just like, and then you can just like start blasting away, like using this like big imaginary algebraic rewrite.
So have you heard of what's called the matrix?
No, I've not matrix code.
Oh, so this is like the machine learning. Okay.
Okay.
Because if you're, I don't know if it is anymore.
Okay. It used to be maybe like 10 years ago.
You're computing gradients by hand.
Yeah.
Do is you write down your own, this big matrix equation. So you need to use a bunch of matrix.
Yeah.
I see.
Yeah.
The matrices that make up.
Yes.
So I was thinking like, well, back up.
Yeah. It just has like a ton of equations about coins. I want this, but for like more things.
Yeah,
Like, more than just coins. Well, I guess coins are really general, but like.
One thing that makes it harder. Like the most concept calculus.
Yes.
So it's that like you. But that there was a. So it looks like I was. Like an annoying amount of.
I see.
Like you need to kind of remember the.
Can you like have like a term calculus for this?
Okay, so there are.
Like he has a paper that's like.
Oh, I haven't actually read this.
This was like, the first things he did after.
It's like a Dan Licata thing, yeah.
Virtual program. Carefully stuff everything generalized image category.
Yeah,
But I think that it's like a term inside the tree.
yeah, I mean, that feels like, I don't know, my PL grade is just like, oh, do you want a bunch of equalities and you want them to be proof relevant, just like start like adding in. Now, like. Yeah.
So that's what Dan.
Yeah.
That's not useful. Be true.
What it says the type means.
What is synthetic or synthetic category?
There are no meanings.
There's no category.
What are the axioms?
So what is the So like. Okay. Right, so like.
Have you ever done any?
Since
Yes.
No.
It's a category like that, where everybody is a
Yeah.
infinity category, because it's data.
Yeah, sure, so the infinity has to be something.
There's a special type, which is the integral type.
Yeah. Yeah.
Sorry, I don't know what.
And it doesn't form like a.
I have in mind.
Yeah.
And so that follows the synthetic
Oh, I see.
walking arrow.
Yeah, I
don't know what that is.
It's like the category with two objects in an arrow.
Oh, yeah.
So then like, if you have it in your context, like everything you do is now just magically about.
Okay.
Whoa.
I have an arrow, so it's like I'm defining a function.
Yeah,
So you have two of them, then everything you're doing.
yeah.
Anyways, you can do.
Interesting. I see, so it's like, if this is like, oh, I wanna just like go and like break down some programs, because I like programming, and then it macro expands, not just, it doesn't like do the internal language thing. Expands to a bunch of like equalities about morphisms, it macro expands into a bunch of like facts about actual like categories.
Which is actually internal.
Yeah. Yes, but it's like a. It's more meta, where it's like looking internal to like cat or something.
So.
I think you want to analyze a lens program, you need.
I don't understand.
Oh, I see.
There's like some model category.
Okay,
So it's like the category.
You do not have that for any company.
yeah,
Then like,
So
that means that you
full
get
program analysis.
They were like.
yeah.
Get analyzed by-
My mental model for model categories is just like, and then a miracle happens, and then it all works, and it's like, what is happening to me?
And now I will pretend that everything is a space.
Yeah.
Fundamental.
Yeah. I was just. Hopefully.
Yeah.
We abstract away from the detail.
Yeah.
To a reason at a higher level. Well, that's true. I don't like driven by the science of the computation. It's what's on top. So I'm building a type system, but if you don't have a type system, you can write your type. So fundamentally, they just program. They just program.
There aren't variables and there aren't contexts.
Oh.
There are only.
No, they're only types.
Yeah, the types are themselves.
Yes. It's all flat. If you like, I can show you why the type system needs to be separated in the language.
There is a reason.
What do you?
Well, you must.
You like to see?
Yeah, perhaps.
Okay, one line on the whiteboard.
Oh.
Yeah. So, if you want to type lambda calculus, then if you go to type U arrow P, U is a U. T applies to U is a type D.
Yeah.
Right? Easy. But what's really going on is this. If T is a type U1 arrow V, U is a type U. And U1 equal to U2, and TU.
Yeah, what we do.
Right, implicit in the usual type derivation rules, you need equality of time. But if you type the language, you don't have it. So you need meta theory. Go to upward. And then when you need equality of there, do some kind of analysis. No. So even just function time, an analysis of the structure of this time. So in my setup, T is a time T. Is a time U. TU given by the application of the type T. U. This is not the application of ordinary time. This is a program which takes the type T is type 1. Okay. And we'll solve it with all kinds of other stuff too. But the fundamental reason type language sits on top of the term language, which then has other languages on that. Right.
Sometimes. Yeah, sometimes it's not equal to.
Yeah. Even in simple type lambda calculus, you still need to know these types of. You need to turn the types into simple. In order to do it. So if you say everything's lambda calculus, no problem. Another level. One level, you make the syntax using the next level up. You keep doing that. We saw 5. And he says, oh, different version of that. So there's more levels on top. I'm just showing off my different worldview. Yeah. So I say that reasons we need to have types in a. Why shouldn't the computations and types just be computational?
Well, sure.
And the answer is, if you work in lambda calculus, problem. Here's the standard time derivation rule for it's equality. But if you're lambda terms,
I see what, right,
you can't
okay,
decide the
yeah,
equality.
but it's in a sense, actually identical then.
No, but there's no lambda term, it's given two normal
Oh.
forms. Side of third.
Oh, I see, right, okay, and that's what you're saying, yeah.
Program analysis and level. Every time you want to structure of the types or the types of types or the whatevers, up you go. So I have this thing called tree calculus, which programs equality programs is defined.
Then this is syntactic equality.
We have no semantics. Just
Oh,
syntax.
okay.
So equality is the subset. So I can treat the type as trees, as terms.
So somehow applying.
Well, this is a complex operation which takes two types. And a type.
Wait, so this is like syntax, but this is defined within
These
those.
big T's are actually the same big F. Computational language.
Oh, that's interesting. It's
So this is called tree calculus.
I need to use this because I want to hear about that. That sounds cool.
Is that okay?
How do I move this? Okay. Oh, it's not functional at all.
No.
Oh, right,
Yeah.
Okay,
Sometimes it fails.
the issue that we were talking about.
The application of TyDe.
So- If I think the representative will show up, if you doesn't, you just time the, yeah.
Okay. And if you chose like can we squeeze it?
Yeah.
Okay, so I
We just, right, so we just communicate with the speakers and you say, okay.
The truth.
Usually, and yeah, so if I was just doing a keynote, when we have like several speakers, is it my job or is it job like keynote? Is it my job or the job of the speaker?
You want to the share?
I'll yes.
But you don't the share. The sublanguage.
Alright.
Great.
Working on some kind of experiment, a few dozen examples, complex examples, always done. You have to understand the halting problem, it's a manifestation in fixed points, and then work really hard to build. Right. Oh, right. Okay.
So this tree compass, is it sort of possible to write it in an easy way, or is it?
Yeah. No, it's the syntax. It's syntax that's following.
Okay, right. Oh, okay. So the combination. I see. Right. Right.
And since there's only one operator. All the programs are binary. So we need to self-evaluate.
I mean, obviously, it's not meant to be understandable if I look at it, but like,
But you can see it's a binary tree, right? you can see that if you represent a self-evaluator voting as a natural number, then you get a long string of numbers. But the structure is.
But didn't you say that this doesn't have semantics? It's in fact.
Well, when you ask what is the semantics of the program, the answer is the program is up. What do you need to explain? But it's functional.
Well, I mean, I kind of mean like this. I agree to these things. Well.
Okay,
I don't know how to
so I can tell you the reduction,
Okay, sure.
right? There are two versions. So notice a ternary operator. If the first argument is a node, then it's like the K operator for compensatory logic. Okay. If the first argument is a stem, then it behaves like the S operator of compensatory logic.
Okay, I see. So it's
Then we have all the expressive power of common logic and lambda.
well accepted. It's not.
It's all the expression, right? If you believe that combinatorial logic and lambda calculus are equivalent. But there's in this case, what we have here are three isomers. So I'm going to use W to analyze leaves, and X to analyze stems, and Y to analyze form. This thing is this thing is X Z. Shift pattern.
Sure. We got some. Yeah.
So this is the case analysis. If you see something of this form here, then it does case analysis on this diagram. Value a leaf, a stem, or a soil. So this is program analysis. But all the extensionality of combinatorial logic and lambda calculus in the first two plus program analysis.
That's pretty neat, actually. Wait, can I have a look at this picture of your?
Yeah, sure.
Sure. I wonder if I can identify some key things. But.
Right. The point about this picture is it shows that the modularity of the program is captured directly without any notice.
Yeah.
The meaning of a form is.
So the thing at the top where it says Rebecca is some sort of like.
Well, this is the
Something
picture.
like right.
This is the physical operator.
Yeah. And then.
Like,
So when you just things to evaluate, yeah.
so when you have say I've got a tree, want to apply to another tree.
Yeah.
You just.
Suppose this is a fourth. Well, now it's got a third branch.
Oh, I agree. Okay, yeah,
So now I
yeah.
can reduce.
Is there any particular reason? So is this something you designed then? Yes. Is there any particular reason why it's I think that's a simple way of doing it, but you could presumably.
Okay, so I tried to work out how many count you have with a single operator, ternary operator. I'm easy to work on. Hey, Barry. Hi, how are you, sir? Very good. And I thought the kids, you have a different first name, yes, yeah, sorry. I have a pen, maybe I'll, yes. Yeah, so I reckon that if you have a single ternary operator, and you're allowed to mess with any of the arguments. Or count as in the universe.
Yeah.
So this is inspired by trying to, well, you know, that is to capture the S and K combinatorial logic plus some more stuff.
Have you used this? Have you? Is this kind of obviously not a hugely practical way, but it's something that you compile from other language to, or you would never be practicing this, right?
So in my career, I have implemented self-interpreters for a few languages. Each one of them has had 0 use. So I'm not going to do that. All of this stuff has been implemented in and personally that I see if a large language model can spit out down the track. Currently I'm working on type theory.
Yeah.
And you can see that the type analysis.
I guess what I mean maybe is that if this is a really nice way of almost getting around this problem of evaluating every month within themselves, giving a idea of what it might look like if we sort of using this kind of almost underlying one way it might have without this, but we actually look like we
In the raw implementation, I have defined lambda abstractions.
Oh, okay. And this was mapped into the
Yeah. It is. And in fact,
and the sort of case structure.
Yeah,
I guess that's quite natural thing right now.
yeah. So it's easily sorted. But I can define things like the size. Take the program and get like a number between the size. So you do complexity.
Sure. Well, yeah.
And can't do in lambda calculus.
It reminds me of, and I'm not super familiar with it myself, but it reminds me a lot of this actually.
Well, but they're all using codings. You can't do the list macros.
Yeah.
So they're already creating levels.
Well, yeah.
So this is a very materialistic setting. There's no superstructure. Yeah.
It sort of makes me really just ask, like, you know, what sort of sounds it do? That sounds too grand a question, really.
Well, my thesis is that it's complete. Lambda calculus.
Is this something which formalizes the question?
Well, the Church-Turing thesis says that lambda calculus is complete computation. But if you look at the product, it says, well, let's encode everything as numbers. And that encoding is computations outside the system. I would say, or accurate statement is that
what is it outside of the system
that this system is complete with program analysis without encoding. That's amazing. Because I can define a self-interpreter.
very cool.
No, it's a thesis. The same way that it's Church-Turing. Okay. Define a quality program. Define a self-evaluating program. Well, there's a paper in Pepper on the type theory, but I actually have a book online.
Okay.
So, marriage, so there's a website, treecalculus.edu.
Oh, okay. So it's not totally acceptable then.
Or it's kind of combination.
Is it just an online book then? Or is
Yeah,
it?
yeah. Yeah, I had a contract this spring, and they couldn't find anybody willing to write.
Right.
Oh, it's too bad.
Well, I think I've never heard of it. Yeah. So there many other people.
Share 200 engineers. Is I mean, software.
Okay.
But they're.
Or the second topic. I
I
don't
think it's
know.
surprising
The first session.
Oh.
So, but what we ask is,
But I mean, it's a software.
The software engineer looks at this and says, no such solutions.
Oh, yeah, I see. It's just usual.
Maybe we think we've been software.
Do you want to
Uh,
use the?
Well, a few hundred.
Yes.
Fair enough.
Yeah.
That makes sense.
So, yeah.
So, sorry.
No problem.
Oh, sorry.
So let's just double check. Oh, the time's up. Okay, that's fine. If you can send them to anywhere at this point, find it. Licensing. So maybe. Or if you have a memory stick, then that's so yeah. Either way, it's perfectly fine. From I think you just make that up. Oh, yes, it is. Mark off. Yeah, okay, brilliant. Wait, I actually want some.
Oh,
I'm doing the other speaker. Actually, sending email. Use record, re-record. That's why it's. I'm sorry, I think it's in the message.
Oh, at Mark 4. Right, missing. Yes.
Yeah, he responded.
Sure, okay. I won't be here for that one. You have a different volunteer.
So do you
But I
know
can.
how to send the drive?
Oh, okay.
Re-record.
Oh, yeah, so that's totally fine. So what you will want to do is, so there's this topic on, it will say obviously, but it's done. You just want to add it in. Oh, yes.
You'll see it.
I just saw the website.
Oh. Really? What is like? She's also the president of the session. So I'll be doing the slides after.
I just well,
You just upload, wait, so which talk is yours, sorry?
so
Oh, okay. So yours, okay. Oh, you're in the afternoon session?
yes.
Okay, in that case, I'll add, yeah, if you can send them to me somehow, I'll add them to this folder. But then, yeah.
I uploaded my slides using the mixture job.
Oh, where have you uploaded it? And it's, sorry, I just sort this one out, but. Sorry. Yeah.
maybe she's amazing. Maybe you need to copy some.
I mean. Yeah, and. But maybe if you actually. Something. A little bit.
Yeah.
I don't know, you can.
Hello?
You're sitting in chair.
Yes.
Okay.
Right. Fine, yes. Okay, we should go to the now. Hello, yes.
Hello?
Yes, really.
This was, helps you in terms of slide and just. Let's hope my system. You're all good. I think we're making sure there's something live.
Hello, hello. Hi.
I love it.
Oh.
You know? Oh, yeah. Oh, yeah, of course. Yeah. We were. Oh, okay. Okay, so we order something. Let's get us. What's the birthday teacher? That's what I'm gonna think. What's that?
Okay. So if you want, I can share my slides. So we can check if you can see it. Okay, that's perfect. Thanks. So I assume that now you can see and listen to me.
Remember the airport. Yeah. It's like, I was already sharing.
No, nothing. I just say that now I assume you can see me and you can also hear me.
You're
That
much better
since
than.
you didn't.
Oh, I've got an idea.
In the airport. Yes. I feel. Yeah. So like, I was like. I
Yeah,
guys
I mean,
had
we could do
this
that, but you could
like.
say that's-
Where being guy.
Right. I feel online. Yes, I don't know. That's very much. I'm Chester. And you're
I'm junior, but like I prefer to use name Claire because no one can actually Claire. Yeah, no one can actually pronounce my Korean name, so I don't care about the Korean name.
this week.
That you guys are.
You just hear that, like, whatever you guys are saying.
Oh, do we have an echo?
Yeah, there's a little bit of that.
Oh. And anything?
Selectively. Yeah, yeah. That's yeah. Oh, I know. Hello. See, with my. And also. People and. You never gonna find out it's great. So just we were right. We look some yes. Fucking yes. Oh, you're. Thank you. All right, welcome back to the so hi. All right, so welcome back from the coffee break. We've got a few talks in the second session. This foreshadowing for the something about co-natural numbers. Sorry. No worries.
Cool. So this first one, Marcos will be giving this talk, and it's one near and dear to my heart. I teach data structures at Indiana University, so I'm always teaching about binary search trees and ABL trees. But I do it in Java. Oh. And so I'm really excited to see sort of how to do it in a nice way in Haskell. So great. Thank you, Marcos. Go for it.
Well, thank you, Jeremy. I'm not sure if it's gonna be a nice way, but let's try it. Well, as Jeremy said, my name is Marcos Viera. I'm from Universidad de la República, Uruguay. This is a joint work with Nicolás Rodríguez and Alberto Pardo, also from Universidad de la República, Uruguay. Alberto is here around. I don't know. Is there any problems? Are there any problems? Hello? Okay, so I don't know if you're here my presentation, but I won't bore you more. So yes, this is a joint work with Nicolas Rodriguez and Alberto Pardo. Alberto is also here in Zoom. No? We are at Uruguay now, and this is a work we have done doing some experiment on how. Oh, okay. No problem. Do you hear me? Hello, hello. This is the problem of being so far away. Okay, John Min said he can hear me. I think Alberto can hear me too. Do you? Okay. No, I don't. Let me check if there's something from my side. Or then... Hello, hello. Okay, I will say something. It is okay now. I don't know if I have to be mute or it's okay. It is running okay now. Okay, let's go there. Well, as I said, representing data structures with invariants in Haskell, we will use BST and ABL as use cases. Okay? Well, data structures are typically defined by a series of invariants that the operators must reserve. Yeah? And this leads us to the question, can such invariants be automatically enforced by the language we usually use, in our case Haskell? Well, in functional languages like Haskell, we are able to ensure structural properties about the data. For example, we can ensure if that a tree is binary. But generally, we are not our languages are not expressive enough to encode at type level some semantic invariants. For example, if a sorted list is really sorted. Yeah, this is usually the work we do with dependently typed languages, not with Hindley Milner languages. But since nowadays Haskell has introduced some extensions that don't provide proper dependency type in language programming, but do provide some kind of type level programming, we have experimented on how to encode and enforce invariants at type level in Haskell using such features, using type level programming. And we used BHT, binary search trees, and ABL trees as case studies. So in this presentation, I will focus on BHT, but then I will just try to talk just a bit about ABLs too. Yeah, we have followed 3 approaches on how to encode and verify environments, and they have somehow incremental rigorosity. The first approach, we call it fully externalist, in which we couple the structure with the proof of the invariant. Then we have another approach that is called internalist, in which we prove the preservation of the environment by each operation that modifies the structure. And then we have an internalist approach in where the invariants are encoded in the data type of the structure. Yeah. But before diving into explaining the approach, we have to see how we can encode some information in the data types in order to be able to check those environments. Yeah. So as I say, we will use binary search trees as a case in this presentation. Binary search trees, I think everybody should know them. They are binary trees which have an ordering invariant. Yeah, and the ordering invariant is that every value in the left subtree has to be less than the value on the root of the tree, and every value in the right tree has to be greater than the value on the root of the tree, and this is recursive. Yeah. So usually in a language like Haskell, we encode those data types in a type like this, where we have like two constructors for the tree, one that can allows us to construct an empty tree, another that allows us to construct a node with some value of type A in the root and subtree of type 3A and subtree of type 3F. Yeah? Of course, this data type allows us to encode the structural invariant. Let's say, well, it has to be a binary tree. Yes, in this type we encode this, but we cannot enforce, for example, the ordering invariant. Yeah, and so to enforce the ordering invariant, we have to leave some more information about the data structure to the type level, and this is what we are going to do. Yeah, we're going to try to leave the information we need to encode such environment. In our case, we will assume that our trees contain key value pairs, yeah, and that the keys are just naturals. This is just a simple way, a simple example of something that has some information we want to lift to a type level. That is the key, and is in this case the natural number, and some information we don't mind because it's not necessary to check the invariants, sorry. So we don't leave them. Yeah. So we define this key value type to represent the values we store in the tree. Yeah. And look that in this data type we have this type of kind nat. Kind is a type of a type in Haskell. Yeah. So it's a type that is that can be a natural number, but we don't have any value of this type. Yeah, so this is what we call a phantom type. But we use it just to encode this information of the key at type level. And we won't need it at value level, so we will just only encode it at type level. Having this type, we also can define the type of trees which are indexed by trees, yes, at type level. And those trees are of kind tree nuts. Yeah, if you look at the constructors in here, for example, when we have the constructor for the empty indexed tree, we index this tree with an empty tree. And when we construct a tree with a key val and two subtrees, we index this new tree with a tree that is isomorphic to the tree we are building, yeah, but only stores the information of the keys. Yeah, so what we say here is that the keys are reflected at the TyDe level in this structure that reflects also the keys and the shape of the structure. Yeah? So there we have all the information we need, yeah, at the types to be able to check if the invariants are satisfied. So for example, if we have a way to promote a number to the type level, this is example we can do it with a proxy. Yeah, this in here we define a proxy value n0, that is just a proxy, and this proxy is of type 0. So we are like lifting the value 0 to type level. Yeah, and well, with this function we can construct a value key val, saying which is the key and which is the value. Yeah. So we have this, we can, for example, construct this tree. Yeah, this tree has this shape. And we can see that at type level, this is the type of the tree. This part is the type of the tree. This is the index that encodes this information. We are encoding the shape of the tree and also which are the keys for each element. Yeah. So in this picture, you can see that the blue parts are the information that is stored at type level, and black parts are the information that is stored at value level. Yeah. So we have like a mirror, no? Like some of the information of what we have in the value level is also the kind level, and there's also here some information that since we don't need it at value level, we only have it at type level. Yeah. So now let's start with the approaches we have to check the invariance. The first one, which we call fully internalist. In the first one, we pair the structure with a proof that this structure satisfies the invariance. Yeah? So we define this type EBST with that. But to construct some value of this type, we will provide an indexed tree, sorry, with a tree T as index, and a proof term of type EBST indexed by the same tree. If we can construct, and this proof term will encode some inductive proof that the keys are correctly ordered. Yeah, the data type that defines this inductive proof just follows the shape of the tree and imposes some proof obligations in here. So put some constraints. Yeah, say, well, the ordering constraint of this invariant. Yeah, that this is a type family, that is a type level function. And this is a Boolean type family that says, well, all the values in the left subtree has to be less than the value n. No, and we impose that this has to be true. And this says, well, all the values in the right subtree are greater than the nodes in the value n. Yeah. This is the way we define this type family LTM, for example. And you can see that it's just the function here where we compare values and we just want to have those like less than, and less than n, and well, recursively we apply it to the subtrees. So for example, now if we can define a proof term for this tree, then we can couple it in the tree, and then we are sure that the invariant is satisfied. Yeah, remember the type of our tree, of our example tree. For such tree, we can construct this proof. And once we couple them, this compiles and gives us the information that, okay, this is a tree, this is a proper binary, this is a proper binary search tree with respect to this invariant, this invariant. Yeah? And of course, if we provide a wrong tree or a wrong proof, then we get a compile time error. Yeah, and so if we can't construct a proof, or if we construct a proof that something that is wrong, we will get a compile time error. something nice about using Haskell in this case and using type classes is that we can automate the derivation of proof terms using the instance resolution mechanism. Yeah, if we declare a class whose method is just a constructor of something of type is BST T, no, of a proof term, and then we declare the instances that put the proof obligations there. Then if the tree we are trying to prove as a BST tree, it complies with all those proof obligations, then we have for free the proof term, and we have the proof that the variant is satisfied. Yeah? And again, if we apply it to an unordered tree, then this results in a compile time error because those instances won't apply to this tree because some of those constraints couldn't be solved. And then there won't be instances to make this, for this type. And then we will have a compile time error. Looks nice. How do we implement functions for this structure? Since we have a lot of information at type level. Also, in this case, we have the key information at the type level. Well, we have to implement such functions with type classes. Yes, and the instances of such type classes are the functions equations. Yeah, for example, if you want to implement insertion in this BST, we will define this class insert BST, where we have to provide the way we want to insert at type level and the way we want to insert at value level. Yes, and they are coupled in this way. Yeah, because if we insert something of type key value KA in an indexed tree with index T, then we will produce an indexed tree with this shape, and this is as an associated type. Yeah, that is also some sort of function at the level of types. So we perform the insertion both at value and at type level. Yeah, when we insert, for example, in an empty tree, yeah, this is guided by the types, and we say, well, type level, inserting some k in an empty tree will generate an index or a type fork empty k empty. Inserting some key value in an empty tree, well, will generate this fork, yeah, with this empty tree with key value. Yes, and the shapes are isomorphic. Yeah. So we have like in some way to duplicate the code when we are doing this because we don't have proper dependent types. When we have to rely on some type level information, for example, when we have to, for example, to look at the keys and see in which direction we have to go to insert, okay, then we can apply a type level function. For example, here we're applying this type level function compare NAT, that we compare the key and n, so those are types, but are types of kind NAT. Yeah, it will produce a type O, and then we will delegate to another type class, yes, which will use this result. Yes, it will say, well, if you are less than, then I will do something. If you are greater than, then I do something, etc. Yeah. So this new helper type class, it's like the way we used to distinguish cases. Yeah, cases that are guided by type level information. Well, having those operations, then we can construct a type safe BST using this insert BST function. But look, we are constructed here an empty I3, and then we start to insert, then we insert this complete structure, and then we try to make the BST. And at this point is when we will verify if the invariants are satisfied. Yeah. So with this approach, we are not checking if the insertion algorithm preserves the order invariant. We are only just like testing the results. Yeah. So we cannot say anything about the operations. Yeah, all the operations that we are defining. We are just looking at the complete structure we define. So trying to solve this, we experimented with this another approach that is what we call the externalist approach. In this approach, every operation that modifies the tree, we couple it with an explicit proof that this operation preserves the invariant. Yeah, and then look at, so for example, for insert, we will define this insert EBST function that given a tree that we know that is a BST, we will construct a new EBST using the same function that we used in the previous approach to insert, but now adding this proof that the BST will preserve the invariant. Yeah. So, and look that this. Oh, in here we should reuse the data types we defined for the full externalist approach, and we also reuse the operation, but we just add new operation that manipulates the values of type EBST, what are the safe values, let's say, with respect to this invariant. Yeah. How do you assure that this insertion function which preserves the invariant? Well, because here we use the associated type of the class we use it to define the insertion. Yeah, so when in this class proof is BST insert, which will produce the proof term that the new tree is also a BST, takes the key, the proof that the previous tree is a BST, and then will produce a proof that the key produced resulting of inserting BST using the insert operation we defined before is also a BST. Yeah, and this is information we had at type level. Yeah, because this insert function is the function we defined at the type level before. Well, I won't go into a lot of into details here, but we can see that to implement the proof, we need to define instances, and we have to convince the type checker that such things are okay, and we are also using induction here. Yeah. So having this operation, now we can statically guarantee that on each step we are constructing a BST that preserves the invariant. Better. But since we are using type classes and we are using instances, it can be the case that we define the operation, we define the type class, and we omit some instances, and the fact that we omit those instances may not be noticed until we use this insert operation in some tree that needs this instance. Yes, in this case, we will have a type error, say, well, this instance is not defined, but otherwise, we are not really sure that the complete proof is done. Yeah. Going a bit further in rigorosity, we define this new approach, that is the internalist approach. Yes, and this approach where we mix everything together. Yeah, the type that defines the structure and the proof or obligations of the invariant. Yeah. So the invariants now are encoded into the tree type. For example, in this case is IBST. and they have to be checked. So since they are here, they have to be checked any time that the value of such type is constructed. Look at that here we have the proof obligation that we had in the proof type, so that we had in the other approaches. So we can say here that values of that type are correct by constructor with respect to the invariant. Now, when we define an operation, for example, to insert something in this tree, we have like to put together, the algorithm of the insertion, let's say, and also the proof that the invariant is preserved. If you look at here, the code looks similar to both the code of the insert, which I showed before, and the code of insert preserves BST that I show later. It's like a mixture of both. Because we have to do everything together. So we are losing some modularity, but we are like anytime we treat a case of insertion, we also add the proof that this case of the insertion it's okay. So we can say that in some way that this correctness proof is guiding the implementation of the operation. So because we are implementing the operations of insertion or whatever algorithm we are doing on the instructor, but since we have to convince the checker that it's okay, that it preserves invariant, we are like guided by the proof. Well, this is the last approach. All the approach have a drawback that it's since we are putting a lot of constraints in there, the compile time verification increases type checking complexity, and compilation times grows exponentially in the size of the tree. And also there are some runtime overhead because we have proof terms constructing there, and we're using type classes all the time and instance resolution. So it's this way, let's say, of being safe doesn't scale if we want to use it for big trees or big structures. We have to have in mind that this invariant checking, when we are defining in the last approach, we are defining we are trying to check that the invariant is preserved by the operations, is usually during the development of the operation. Once we have implemented those operations and we know that they satisfy them, then we can forget them. So what we try to do is to get like both the best of both worlds. To have this safely when defining the operations, but then don't lose efficiency. And so to do that, we define it as systematic manual translation from invariant-based code to undecorated code. This is the usual code we will write to implement an ABA, and for example, a BST. And in this translation, what we do is to remove all the type level information and remove all the proof term, basically. So how do we do that? Well, we start with a demotion phase. Let's say that is just to remove all this information that was promoted to type level. What I say, for example, we have all these keys that now we need them at type level. Well, let's just put them at value level. So we will lose this type, we will put it in here, and we will lose this index. So this is what we produce, and this undecorated key value type, with this NAT that now is at value level. We also remove the decorations and proof obligations. So, for example, this I am explaining this the translation in the case of the internalist approach, but it can also be used to the externalist approach. In the full external approach, it has no sense because we have no proof of preservation, so we are not sure about the operations. So in the internalist approach, this type, which had the index that was the tree and has all those all those proof obligations, we will remove all of this, and we will end up with the usual way we represent a binary tree. Yeah. In the case of operations, it's also the other way around, as I said, we are doing. Yeah. Every class declaration we use to declare a function, well, we define them as proper functions. So class declarations are function signatures. Yeah, for example, in the case of insert, okay, we don't need now this information about how we insert at type level. We only need information of how we insert at value level. And we are, as I said, losing all this index information. So we end up with this signature. And all the instances we defined are now translated to equations in the function. Yeah, for example, this is the case of the empty tree, and this is the case of the insertion. Yeah, and then we end up with a complete implementation of insert, in this case, in a BST, which, okay, is not the usual one, but it's close to it, and we are kind of sure that it preserves invariant. Yeah. Well, we have done the same, we have applied the same methodology to ABS, which are basically BST with a balanced condition. In the case of the externalist approach, since it is a bit more modular, it was just reusing the same types and adding a new condition that is that the tree is balanced. Yeah, but okay, we have to re-implement the operations because the operations in the ABS are different than the operations in BST. And in the case of the internalist approach, we had to redefine everything because everything was tied together. So finally, to conclude, we have explored these three approaches for representing data structures with invariant in Haskell: the full externalist, the externalist, and the internalist approach. The externalist approaches promote modularity and enable code reuse across different representations of data structures. The full external approach is not does not give us guarantees about on the operations. Yeah, it doesn't see that the operations preserve invariance. In the other way, in the other side of the spectrum, the internalist approach guarantees correctness by construction, but at the cost of reduced modularity. And well, as I said, the major drawback of all three approaches is that this exponential increase in composition type. But well, we showed a poor man of extracting code, let's say, way of extracting code. That is this translation methodology. So I think this is everything I had to say. Thank you very much.
Don't mind if we could maybe skip the question session because we're sort of a little bit behind now on time. Jump into we can do questions offline, perhaps, on Discord. And then we can dive into the next talk. Chester. All right, so Chester is going to be talking about doing some performance evaluations of normalization by evaluation. Better ones. Not better ones. Yes. Yeah. Naturally. Hard mode. Just a reminder, every room light is 25 minutes vision and oh, didn't mean to close that. So, hopefully it works. Hopefully it works. Like, right. I don't know. Just sign in real quick. Do you have an account? Yeah, I do. Oh, that's perfect. Oh, wait, it's on this. Can you not put it on the screen? Oh, sorry. Yeah. Yeah, and here's my password. Blank. Thank you. We don't have PowerPoint on these computers. Are there any Microsoft employees here? Oh, I wouldn't be surprised. Yeah. There's no rush anyway, don't worry.
Hey, Kiana, do you have the duo? Yeah, okay. Oh. To share this screen as well. Yeah, that's fine. Yes. I guess in hindsight, we could have taken questions, although actually we're sort of using this computer. But if anyone has questions, they could maybe message in the Zoom, and if Marcos is still there, then. Oh. Yes. Brilliant. Oh, great. You just signed in. Maybe it will be. Oh, come on. All right, one more time. Is there anything we could do instead? I have my laptop. If you have Zoom on your laptop, then maybe I might have Zoom. Oh, yeah, all right. Is it desktop? Right. That's the laptop. So right. So let me just share screen. If I share the whole screen and then do the PowerPoint, does that work? That should work, I suppose. So if I right, I'm assuming this is working. I don't have Zoom up. If anyone has Zoom up, can you tell us if this is working? But I'm otherwise assuming that it's probably working. Sorry about that, everyone. All right. Good luck. Yeah. All right. So yeah, I'm Chester Gould, all the way from UBC, and we're talking about a performance comparison, syntax, type-directed judgmental equality. I guess a standard disclaimer for PL talks. If you don't know what one of those or many of those words mean, we'll get to it. Don't worry. Does this work? Almost certainly not. Good. All right. So I've come all the way across the Pacific to Singapore to answer one question. That question. So, when I was an undergrad, those many long months ago, I had to work on a research project that involved writing a type checker, specifically a type checker for a dependently typed language. But what is that? What is a dependently typed language? I'm assuming some of you know, but just a little, in case there's someone in the room who doesn't know, we're going to do a little dependently typed crash course. Yeah, all right. Cool. So consider this function. Super helpful. You might write this yourself. If you're trying to give this function that takes a Boolean, if it's true, returns 5, otherwise returns the string hello world, you might try and give it a type. But if you're working in a language like Haskell, you might have a bit of trouble doing that. But with the magic of dependent types, we can give it that type. This type says that if you give the function enter string a Boolean, then it's going to return an int. Otherwise, it's going to return a string. Just like it actually does. Wow. Okay, then we can do that to implement 5. Call it with true, should return 5. But maybe that's not enough for you. Maybe you want to prove that our implementation of 5 is correct. So we can do that. We can do that too. So we define another global variable. And notice that this is its type. So its type is a proof that the global variable FIVE is equal to the number 5. And then as our term that has this type, we use the reflexivity proof. But how does any of that work? Don't be alarmed, but yeah, typing rules. Okay, so what is this thing? Derivation rule. If the thing on the top is true, namely that we can judge that E and E prime are the same, they're the same expression, then we can judge that reflexivity has the type of a proof that E and E prime are equal. But that begs, well, okay, it begs probably more than one question if you're not familiar with dependent types. But one question it does beg is, what the heck is this? What does this mean? So intuitively, you should read this as saying that the expression E and E prime run to the same value. So when we say that we can use the reflexivity proof here, we're just saying that 5 and, well, variable 5 and the number 5, they already run to the same value. So we're saying that this is equal to that 5 there. So you might then wonder, well, how do we know if two expressions run to the same value? So we're going to introduce a few rules. One of them looks like this. This says that if you have an if expression where the predicate is true, then we can judge that to be equal to E, which is the expression in the then branch. We can specialize this rule to our program, a little snippet of it, and we can then judge that that expression that appears in our program is equal to 5. Then we can stack them on top of each other, just like that, and we can get a proof that the if expression in our program is equal to 5. Okay, wait, why did we do, we're on a little digression again. What are we doing that? What are we doing again, right? Yes, type checkers. So, okay, you need to implement a type checker for a dependently typed language. You need to decide on an algorithm to use. Now, of course, being the good undergrad I was, I didn't just like go off and try and hack on something and just implement it, right? I did what all good undergrads love doing. I did a literature review. We love that, yeah. So if you do a literature review, you might happen across this paper by Cocon called An Algorithm for Type Checking Dependent Types. That's a very promising title if you're doing the literature review. So how this algorithm works is that it uses an equality judgment that looks exactly like the one we saw previously. And it works by doing structural recursion on both sides of the equality judgment. So if we were to want to decide if a function application, two function applications are equal, we can do structural recursion. And we first check if the two functions are equal. And then we check if we can judge the two arguments to be. All right, well, maybe, I guess if you're doing a literature review, you don't just stop at the first paper. I guess you could, but maybe I should have, but yeah, so another paper you might find is this one by Chapman, Alton Kirk, and McBride called Epigram Reloaded. And they have a slightly different take on what algorithm you should use. Yeah, we have one guy who knows already. So they use what's called a type-directed judgment, quality judgment. So it's sort of like before, except that we also have the type of the two expressions in the judgment. So this reads that E and E prime are judged to be equal at type A. That means they're both of type A. Now, we still have all our favorite rules, like the if true rule, where A here is just the type of E. But if we consider, since now that we have the type that we can consider, if we have some interesting type like the unit type, which has one inhabitant, open parenthesis, close parenthesis, that's it. That's the only thing of unit type. We can think that, well, any expression of unit type should run to the same value eventually. Therefore, we can add this rule. That just states that everything of the unit type, they're just all equal. So, using our new type-directed judgmental equality, we can do this proof. So this says that this is a function, takes 2 units, and it outputs an equality proof that A and B are equal without even looking at what they are. So the type-directed version, this type checks. It's green, it's great. But in the syntax-directed version, they do not, this does not type check because we haven't even looked at what A and B are. And so all the equality judgment sees is just 2 unrelated variables, and it says they're not equal. So that's just a little taste of how these two algorithms differ. They decide different equalities. Okay, so we have 2 algorithms. How do we decide which one to use? You might want to consider some of the trade-offs. Surely someone must have studied those, right? Trade-offs, yes. What are they? So there are 2 classes of trade-offs you might consider. The first being performance trade-offs. So why might we even think that there's a performance difference between these 2 algorithms? So in the type-directed version, we have this extra argument, the judgment, A, the type. And so you might think, well, on one hand, we now have more information for deciding if these 2 expressions are equal. And so maybe we could complete the search faster. But on the other hand, now we're processing a lot more information. So this might slow it down. What about the usability trade-offs? So we already saw that some programs will type check in one system, some won't in the syntax directive. But when does this appear in practice? When, like, is this actually useful to have these extra rules that we can decide? Maybe, you know, the unit type, it's a bit of a boring type. I don't know. Maybe this code might appear in your code base, but this is not the most interesting function of all time. So maybe there's more interesting types that have rules that the type-directed equality can decide. So without further ado, here's what the previous literature says. Definitively, the performance trade-offs are. No idea. No idea if it's slower or faster. There's lots of debate about this. People have very strong opinions about which one is faster. No evidence for either side. Okay, great. Usability trade-offs, though. Surely someone must have studied the usability trade-offs because some programs type check, some don't. You know, maybe we could find a practical program and show that type checks in one, it doesn't type check in the other. Well, previous literature also says triple question mark. We have no idea.
All these work's been done by theorists, and these
Yeah,
are
theorists.
questions that theorists
Yeah,
ask,
isn't, well,
so.
yeah. Well, we do love our theorists. What? Yeah. Okay, so I will tackle first question. The usability question, that's a little beyond my pay grade, but so to do that, to decide to address the performance trade-offs, you need to do a performance comparison. right? I guess you could try and do a proof and stick to the theory and prove the complexity or something crazy like that. So we need to do a performance comparison. And that means we need 2 implementations, one of each algorithm. Luckily for me, someone had already implemented the syntax-directed version quite quickly. It's quite efficient. See, it says high performance right here. Yeah. So this is by, I'm sorry, I might butcher your name, and I don't know if he's in the room, but this is by Andras Kovacs. And yeah, so that's one. And I will, yeah, so I'm gonna boldly and proudly lie to you all and say that this is the type of the equality decision procedure in small TT. So it takes an expression and another one and decides if they're equal. And so, as I said before, this proceeds by a structural recursion. And so we can just add maybe the add case from that rule we saw before. And yeah, we just do a recursion, check if f and f prime are equal, a and a prime are equal, and if they're both equal, then app is equal. Easy peasy. So that's a syntax direct implementation done. That was, well, not much sweat on my part, but I'm left with wondering, what about the type directed algorithm? Well, I implemented that. So I forked small TT and I modified it, leaving all the optimizations that small TT does in as untouched a state as possible to make the comparison accurate. And in that implementation, my forked version, as again, lying to you all, this is the type of the equality decision procedure. So, like before, it takes 2 expressions, but now it also takes a type. And so, if we wanted to add that unit equal rule from before, we can just add it. We can just look at the type. If it's the unit type, great, they're equal. Super easy. So we have 2 implementations. Now we need to benchmark them. Yes. Hold on. Wait, we need a benchmark suite, right? I can't just, well, luckily small TT actually comes with that and it's pretty good. It's basically just some enormous files for you to type check. The church encodings of the simply typed lambda calculus, it's not super important. Don't worry about it. Okay, great. Benchmark suite. Benchmark them. So these are the performance numbers. And we have the syntax-directed algorithm normalized to 1 in red. Is that red? It's red, yeah. And then we have the type-directed algorithm in blue. And yeah, so definitively, from these, you can see that syntax-directed is faster. 100%, right? The end, good job. All right, we're done the presentation. No, I'm kidding. So these are the tentative performance numbers. This is definitely very much a work in progress. I did my best to keep all the optimizations, but the algorithm it's non-trivial, and honestly, small TT does a lot of other things that I'm just not telling you about, like unification and collaboration and all these things, and maybe my implementation missed something. So this is, yeah, still work in progress. As we can see here, this bar just keeps on going. It just goes off the screen. Yeah, this benchmark did not complete. I think it ran out of memory. Honestly, I'm not quite sure why. That's future work. I thought I knew, and then I was incorrect. Okay, so great. Yeah, future work. Okay, I don't want to be greedy, so honestly, this is our future work. So the first is to take the 2 implementations, small TT and my version of small TT, and just try and optimize them even more. Maybe I missed something, and the type-directed version could be made much faster than the syntax-directed version. I'm not sure. some more future work is maybe your own pet favorite algorithm is not represented here. And you are so sure that it's gonna be way faster than the other two. Well, then you should go and implement it. You should also go and modify small TT or implement something else and show the world that you're right and it's faster. Okay, finally, I didn't address this question. That's honestly a harder question to answer than the performance question. So, wait, what are the usability trade-offs? We saw one rule that's different between the two systems. Is that rule really going to be so important in practice that two things of the unit expression are going to be equal? Probably not. So maybe, yeah, we need to address this, find some use. Maybe there is something that's really useful that you can do with the type-directed version that you can't do with the syntax-directed version. Finally, I would like to give a shout out to another project that's sort of doing a similar thing. This is the benchmarking proof assistance GitHub repo. If you really didn't like the approach I took and you want to go and contribute to the enemy, you can go and do that. And yeah, go and contribute to their project instead of mine. Okay, great. Yeah, so in takeaway, you should know that trade-offs. You should know what you're doing when you're choosing between two algorithms, and instead of just being very opinionated about it. And yeah, great. If you're interested, there's more in the extended abstract, a little bit more. Yeah, thank you.
We've got time for questions.
Do I get to choose? Yeah. I did. Yeah, we didn't even, yeah, I lied to you so much in this talk. I didn't even mention normalization, did I? But it's in the paper. Yes, I reused it. Yeah.
Your equals has an expression type to boot, right?
Yeah.
You check that both expressions actually have the type before.
Yes. So yeah. So yes, you in the type checker, you first type check your two expressions.
Mm-hmm.
If you know, you have to know what their type is beforehand. Check that their types are equal.
Mm-hmm.
Using the same procedure because we're independent types and types are yeah. And then you get to check them. Yeah. Yeah. Cool. Any other? Oh,
Okay.
Yeah.
So like this is just hearsay, but my understanding of András Kovács's work on small people is that like he doesn't just write the Haskell code, right? Like he actually looks at the core. There's a ton of micro optimizations that go into
Yes.
My question: did you just write Haskell code, or did you try to put in the same effort? Because otherwise, there's a huge difference in the engineering effort between.
Absolutely. So yeah, so as I said, I totally lied to you about the type of that decision procedure. It's doing some stuff in the IO monad with mutable states. All his optimizations that he does, I did my best to port them to the type-directed version. And I did my best to not write slow code. I have some experience in Haskell. I tried my best, but I mean, honestly, I think that's the best answer. Yeah. Yeah. Of course.
Is it more efficient would be combine the type checking with the
sorry, combining type checking with what?
What would you just said is there are two expressions. First to the type checking for two expressions and the
I hadn't thought about that. That's an interesting idea. Implementing. Yeah, I mean, yeah, this is just sort of a propaganda, like get people excited about this sort of talk. So yeah, that's a great idea, and we should totally implement that. Sure, and then I'll get to you.
No, just to follow up. So the type of your equality function was something expert. I know it's a lot.
Yeah.
It's like expert type do.
Yeah.
And like just the order of the parameters kind of suggests that you are looking at the terms, and then you might use the type information.
Oh, okay, yeah.
Make progress. But
Maybe I didn't mention. So yeah, so that algorithm, it proceeds by a structural recursion of the type first.
Okay.
And then the expressions. Yeah, I guess it's Curry's, it suggests something. I'm not trying to suggest anything. I just wrote it that way. I think it's the same. It might be the other order in the actual. You had
Just to note, it's, you said that the unit type, equality judgment is perhaps not that useful. So like but if you have peripheral elements.
Oh yeah, peripheral elements.
Lots of things that are basically unit types.
Yeah, okay, there's one use case. Yeah, okay. Yeah, but then that sort of begs the question. Is peripheral elements useful? I'm not saying either way. You just yeah.
You have a type for the meeting, thinking. You have a type for equal function type?
Yeah, there's a it's just the like ADA rule. It actually turns out that both systems can decide specifically for function types and for the dependent pairs. They can decide the stronger ADA equality for both of them. But it doesn't work for unit types. As it doesn't work for there's some other types like coproducts. Yeah. Did we do it?
All right.
Yeah, answer. Yeah.
Thank you.
Thanks.
Got the co-natural numbers.
I did join the meeting already, but I had to leave because there was an action. What streaming? Yeah. And so yeah, arrow keys to 5.
Okay, hi, I'm Sumi, and I will talk about our formalization of co-natural numbers forming an exponential commutative summary. And this is joint work with Victor Benche, but sorry. Oh, do I need to?
Yeah, I need to.
Oh, yeah, thanks.
Oh, let's just place this in.
Yeah, brilliant. Thanks. So first, okay, I hope people are familiar with the inductive definition of natural numbers. We have two constructors, zero and successor. Yeah, but okay, there's another way to define natural numbers, which is to have one constructor, which takes a maybe of natural numbers. So we can represent zero as like using this constructor taking nothing, and successor as taking just. But okay, we can sort of, so everything in like type theory and category theory have like dual stuff. So maybe we can like dualize this. So instead of an inductive type, we could have a co-inductive type. And then, so here we have co-natural numbers. And this is how we write it down in Agda, but there are some idiosyncrasies of Agda syntax. So what it actually is that this conat is an co-inductive type with a single destructor, Fred, taking a predecessor for connatural number. So it's a function from conat to maybe conat. And like we say that if like a connatural number doesn't have a predecessor, then it's like 0, and then if it has a predecessor, then it's a successor of something. You could think of it like that. So yeah. So let's look at some examples of connection numbers. To define values and functions involving co-inductive types, we need to specify what the predecessor of the returning value is. For example, we say that the predecessor of 0 is nothing because it doesn't have a predecessor, and predecessor of suck is just x. And then we see here, we can also define infinity, where we say that the predecessor of infinity is just infinity. So here we can see with co-inductive types, we can define infinite structures where we're taking like the projection of the destructor, we still get like the same thing and goes on forever. Okay. And the goal of this project is to define the exponential commutative Semmering structure on connection numbers. So what is that? So we have 3 binary operators, addition, multiplication, and exponentiation. And also 0 and 1, that's 2 values. And then it needs to satisfy these equations. On the left, you see like the equations for commutative Semmerings, where V plus is like associative and commutative, and also has a 0 as an identity. And same for multiplication. And there are some distributed laws. And then we also have some equations for exponentiation. And these equations should be familiar to you from like maybe high school, I don't know. But because like natural numbers also form an exponential commutative Semmering. Yeah. So now we want to do it for connatural numbers. Okay. For the rest of this talk, yeah, I will show a naive attempt of doing this and show why it's not good. We need some better ways. And then I'll briefly talk about one way, which is to use the co-recursion principle and think hardly about what the internal states of this should be. But then we'll see that this also doesn't scale very well. So next, we'll look at a technique by Niels Anders Danielsen of using embedded languages to help with this. And then the last approach is based on this method, refining it. And then in the end, we have formalized the full commutative Semmering structure, exponential commutative Semmering structure using the last method. Okay. So let's see what the naive attempt is. Okay. So we could like define addition, try to define addition. And okay, we need to specify what the predecessor of x plus y is. First, we match on the predecessor of x. So if it's nothing, that means it doesn't have a predecessor, so it's 0. Then we just return the predecessor of y. So predecessor of x plus y, or predecessor of 0 plus y is the predecessor of y. And then if the predecessor of 0 isn't 0, then the predecessor of x plus y is x minus 1 plus y. Okay, so we can get the x minus 1 from the matching on the predecessor of x. Yeah, and so far this is actually good. Agda accepts this, or yeah. So I'm doing all of this in Agda. Yeah, Agda accepts this, and so Agda is happy. But let's look at multiplication. Again, we specify what the predecessor of x times y is. And then we just match on both the predecessor of x and the predecessor of y. And if either of them is nothing, then we return nothing. So this means that if you multiply 0 on either side, then 0. And if neither of them is 0, then the predecessor of x times y is this y minus 1 plus x minus 1 times y. But if you like add 1 here, then you'll see that it should be equal to x times y. However, Agda isn't happy. It says that the termination check has failed. And why is this? So Agda implements something called guardedness for co-inductive types, which means that all the recursive calls need to be under constructors. So here, this is the recursive call for multiplication, but unfortunately, it's an argument to this addition function. And addition isn't a constructor. But this function is actually good. It's just Agda's termination checking is too conservative. But so we will find some way to overcome this. And we had the same problem when we tried to prove things about natural numbers. For example, the commutativity of addition. Okay, it's just here's the recursive call, and there are some application of transitivity that you need to use around it. Okay. So next, we have this approach of defining good internal states. And what are internal states for co-inductive types? So all these guarded co-recursion can be represented with can be written using the co-recursion principle, or this is also called the unfold function. So here we take a stepping function, s to maybe s. This function can change the state, and it can also terminate. And we also take an initial state s. And what this does is basically applies this stepping function repeatedly until it reaches nothing. And the connatural number that you get from this is the number of steps that you use the stepping function until it reaches nothing. Yeah. Okay. So we have so here I just show the idea of how to define multiplication using this. So the internal state would be a pair of connatural numbers. And then, for example, if you have 4 times 3, then first we would still check whether either of them is 0. And then we can start with the initial state of 3, 2, so decreasing each of them. And then at each step, we decrease the rightmost number. When it's 0, we reset the rightmost number and decrease the left number. And if we count up the number of steps, this is 11. But we could just add 1 at the beginning, and everything's fine. And you can also do this for exponentiation. It's an interesting puzzle, so I won't spoil it here. But yeah, and then you can do something similar with equations, but there you use something called the bisimulation principle. However, if you try to do that, then you get some diagram like this, where you need to relate all of these numbers. So so from this you might see that it doesn't really scale. So this is a commutative multiplication, and we didn't do the so we were able to do the semi-ring properties, commutative semi-ring properties, including this commutative multiplication, but we didn't do the exponentiation because of how complicated it would be. Okay, next approach.
That was all to address the termination issue. Is that what you were with the code recursor?
Yes, using the code recursor, then you don't need to explicitly do recursive call. So this will always terminate if you use this. Okay. Next we have this embedded languages approach. So this is just the technique developed by Danielson, and here I just summarize the method for using it on like defining multiplication for connection numbers. So we define a type of expressions where we add the addition function as a constructor on expressions, and we also have this embed, which embeds like some nx, which are like head normal expressions. So you can take head to see whether it's nothing or just. But so crucially, this needs to be co-inductive to allow for like infinite expressions or expressions with where you have plus and then it needs to be guarded by successor or it has zero. So here we can write zero successor and then we allow this to be. And these two types are mutual. So this is actually something called a mixed inductive co-inductive type. But yeah. And then we are able to define a function for connatural numbers to these expressions just by co-induction, co-recursion, and also define a multiplication function that takes two connection numbers and returns that expression. And here you see we match on the predecessor of x and y again. And when neither of them is zero, then we have a recursive call here. However, now this is fine. Octa allows this because this plus and this embed are both constructors. No, in this language. But we've only defined this multiplication that returns the expression, so we need to interpret it into connection numbers. First, we define a predecessor function, which takes an expression and returns maybe an expression. This can be done just by recursion, structural recursion. So here, pred x and pred y are the recursive calls. And for this case for addition, you might also recognize this as when we have defined a naive version of addition. So it kind of duplicates the definition of addition here. And we also have this interp, which is just repeated applying pred e as like the stepping function for the recursion. But using this, we finally have multiplication. Okay, as like a example, we can look at like the trace of what happens. So the internal state is now the language that we have. Yeah, so from 4 times 3, if it decreases 1 time, it becomes 2 plus 3 times 3, and so on. Yeah, so we can also do the same thing with proofs, with the equations, where we define a language for that. So we have some embedding of these from some normal equations. And then we also have reflexivity, symmetry, and transitivity, and some congruent stuff. But okay, so when you interpret this language of proofs, then you also have some duplication because you need to re-implement this congruence of plus, for example. So there's an idea. So I have an idea that what if we just put all of the operations and proofs into a single language, or operations and equations into a single language? Then we don't need to separate these languages that have separate interpretations that duplicate stuff. So yeah, here we just quotient the language with the equations. So we still have the annex as before, and then we have this type of expressions where we have the addition, multiplication, 0, and then some equations. So we add all of the exponential commutative summary operations and equations. And we also have this embed and some two equations that help us later. But so with this data type is actually, we can try this down in normal algebra. So our formalization is actually in cubical. And also in normal algebra, we cannot prove any non-trivial properties of co-inductive types without postulating the bisimulation principle that I mentioned before. So yeah. Okay, so this is what I call a mixed higher inductive co-inductive type, because this is a higher inductive type and that's mutually co-inductive. And what makes it weirder is that these two constructors depend, the type of these two constructors depend on the structure of that co-inductive type. Okay. Next, using inside this language, we can define again the predecessor function, and here here everything is by recursion, and now the definition look, the definition of addition and multiplication look basically identical to the naive version. So, but Agda accepts it because everything is a constructor. And also, I mean, it's not even co-inductive, or not even recursive functions, so it's fine. So even for proofs, you can also use transitivity and everything. Okay, having this, we can again define the interpretation function using the pred. But thanks to the two constructors that I added before, so these two constructors relate the predecessor function with either 0 or 1 plus value. So using these two constructors, we can actually prove a round trip. So we can embed connection numbers into expressions, and then we can prove the two round trips. So expressions are actually isomorphic connection numbers. And so how do we get all the operations and equations? We first define like a record that contains all the operations and equations. We trivially have have an instance of this record for expressions. And then we can just use this isomorphism. And in typical, we have this univalence axiom where we can transport over equalities or isomorphism. So from this, we get this automatically from just one line. Yeah. Although actually you can also derive this without univalence. However, it's much more work. You need to do stuff for every field that I have in this record. Okay, so in conclusion, we have formalized Conan members forming an exponential commutative summary in cubical algebra, and this is also like a showcase of a practical application of cubical algebra and also univalence. And okay, so we tried like different approaches. One using co-recursor and bisimulation, which I didn't go too far into, but here we proved that Conans from a commutative summary, and it doesn't scale. Next, we used this quotiented embedded language, and we proved everything that we wanted. However, there's one problem that it's not modular. So we have this huge data type. However, if we want to add more operations or equations, we must modify the data type and modify the whole proof. Yeah. Okay, so there are some open questions. Like, is there a way to prove this that is both simple and modular? So simple like the second approach, but modular, or like the first approach where we didn't rely on anything. Okay. Another question is, like, is there a way to define more complicated functions like titration or like the Ackermann function? Like, it's not clear what kind of internal state or what the predecessor of like titration of two numbers is. Or so, and then lastly, so I use this mixed higher inductive co-inductive types. However, this is another one of these crazy data types that Agnes supports. So we are actually not sure what the semantic justification of having these are. Yeah. Okay, and this is it for my talk. Thank you.
Using Gaussian type theory to model these functions or maybe Gaussian character.
Right. So there are like these fancy extensions of type theory, like guarded type theory, or like also size types, which might help with this. We didn't consider those. We try to just do like, okay, not as vanilla like that because this is still pretty fancy like that, but yeah.
I think that's the nature property is explicitly discussed in the literature regarding Gaussian type theory. That they claim that is the co-inductive type reason type theory could be modular. Because we only have one implementation and have to try that. So.
Yeah.
You mentioned that Anchor doesn't really
right?
Maybe beyond the scope.
It's the same reason that you don't have function extensionality. Yes, in cubical like that we can prove all of these properties. Like we can also prove the bisection of this. Yes.
In cubical like this, are all infinite coordinates equal?
Yes. Yes, so the elements of collection numbers are just all the natural numbers plus infinity. However, this is not actually isomorphic to net plus one.
Question. You're doing the proofs on the quotiented language.
Yeah.
Was that pretty much like normal syntax of proofs in Agda, or was it like more verbose than usual? I'm kind of thinking of some of the things I've done, and I ended up with some very verbose proofs.
You mean
that's
like,
just this? Or no, like proofs about the equations. Like
I didn't include them. Oh yeah, I had this, but I'm lagging here a bit. So
okay.
Yeah.
So is this for the quotient?
No, so I have omitted a lot of stuff here,
right,
and also like this doesn't actually fit with this.
But like, so for the quotiented one, is the proof? Do they look similar, or are they quite a bit different? Like,
no, it's actually basically the same as the naive one. So all of the proofs and operations that are here are the same as naive one. So that's like an advantage of this method. So you can also add an is set here as a constructor. Yes.
I don't need to do induction over explain.
You're doing recursion or also induction is a one dependent predecessor. switch to. Oh. Yeah, this sub is the function that we are defining currently. And when this is called co-pattern matching, where we yeah. X minus one below our variables. So X minus one here is variable that you get from. Yes. So this is actually set truncated.
Where do you need UIP? Where do you need in the that it is a set?
Yeah.
These are equations somewhere.
So so to derive the isomorphism, I had to like prove some equations about this Pratt function, and there I use UIP.
And if you don't have this, you can still define the commutative semitic structure, or do you need UIP?
Probably it doesn't need the truncation.
But wouldn't you get into trouble when you're defining PredB over the equations? Because that might prove that those are also respecting the equations if you're not in a set.
So here, that is fine because that is you do the same thing when you prove the equations using the naive method. You are proving that they preserve the Pratt function or the predecessor, and here you are doing the same thing.
That will finish up our Q&A for now. And of course, thank you very much. Be back.
Thanks. And thanks for the help.
No worries. Yes, I was going to say, you definitely should do.
Yeah. So you have a branch of PredB that where the argument is an equation.
Okay.
Yeah,
But then you will also have to that the equation that branch is equal.
I'm sure.
to
Yeah. So
the other equation.
We only have one differential equation. We don't have higher.
Yeah,
Yes,
no,
but
perfect.
if you don't,
Although actually saying that we did have a problem in USB.
So,
but it's worth a try.
Because
Sorry, I have to run.
See
But,
unless it does
basically, so you'll have a different student volunteer in the afternoon. But what you need to do
just
is
as like
get it into
closes
this
off your
folder.
function definition. That's been my
Then that will be
experience. And
perfect.
I tried using it and accidentally forgot to make something.
Of course.
yeah,
I did a new.
you don't have this problem if you only define functions. But when you come to define equality,
I would say,
Oh, I see. But
higher.
right.
easiest way
So
to
you're not
send it.
moving anything about X until you get to the equivalent.
we
I am actually,
we
but
tried a
only for
USB
the
stick and
equivalent,
it
the
didn't have it.
Yeah. Okay.
We tried sending it through Zoom and it corrupted the file. What we ended up is using my laptop.
I mean, I know that
instead of Discord, but that's because we were trying to do it really quickly. So I guess.
How did you get them there to begin with?
Oh, so the original ones here, these came from the like slide upload.
Yeah, I did that again.
And so I guess one of the AV people would have just downloaded them. My guess is that.
I thought that it was the regular Dropbox.
Yeah.
Oh, if there is still one of these up, then that might well work.
Yeah.
That might
Maybe
well
I'll get one of the AV people to be like, okay, where's the Dropbox?
Okay,
There must be like
I haven't
Dropbox
considered what
access
these
on here
operations
somewhere.
and equations.
I'm a little surprised why they didn't just have it
Or like
directly.
connection dimensions. That's how you could think about that.
Here it is. Wait, this must be it then. This must be it.
As programs
Actually,
that
it just happens to be
Okay. Good, if you just scroll down, maybe.
So have you
Yeah,
uploaded it to it?
yeah, I did.
Oh no.
Oh.
Oh, I think though that there is. They said that I'll have some credentials. Is it maybe? There were 2 sheets of paper on the other one.
Well, something but we'll see what happens. So you've got the semi ring, and then
sorry.
trying to get back into Dropbox. Just by zero. And whenever you've got two non-zeros, it will always multiply. That should be great then. And if you get that, the whole numbers. Yeah. Yeah, because any two non-zeros multiply, then you get lots of round. So then there's this automated procedure.
You'll have a different student body.
Thank you for your help this morning.
There are a few problems.
Yeah, no, but we got through them.
We got through them.
And we ended only 5 minutes late.
We did.
That's pretty good.
I don't know how that happened, but
I think some of our speakers were a little bit shorter, which is nice.
It's a great goals thing. I mean, so these core-natural numbers are also called extended natural numbers. Yes, but I'm not familiar with.
I would say input would rather be here, unfortunately.
In the field of fraction, yes.
Yeah.
In the field of fraction construction into true relevant goals. The Wikipedia entry is very okay. Wikipedia isn't always very always main things in the world. Okay.
I just wonder, in the last page on the last page of your slides, you said there's no semantic justification for higher inductive, higher inductive conduct tablets. But do we have even the semantic justification for inductive conduct?
I think so. So I think about them as the greatest fixed point of these. There's a greatest fixed for wrapping of these fixed points.
Yes, yeah.
So you can also, it's also like the terminal point are also inductively different.
Oh, I have a new video.
New video?
Yeah, that need to be uploaded.
Yeah, I haven't uploaded.
I haven't do it.
Yeah, I think you need to upload.
Using the.
If you're using the link that I think, yeah.
Okay, let me check.
Yeah.
Time account and go in.
I haven't tried doing something else.
So you can like factor out the point. No, factor out the inductive type to take out like the co-inductive parts as like parameter 2, 3, 1, and then the co-inductive type is just using this inductive type and in the parameter you use the co-inductive. I think.
No, yeah, I don't know. We'll check out what. I think I tried this.
So in which
you saw the time together.
wait. I'm not sure what the setting are talking about. In what categories you are starting these two?
In what category?
In what okay, so you have mixed inductive and conductive types, right? So if you do it in more naive set or like category set or other categories is for inductive type is always like an initial sequence for this, and for conductive type have the terminal sequence. But you have two different functors for inductive and conductive. How to actually define the functor else is
So first you have a functor for your inductive type. Co-inductive type set of co-inductive. You don't need the inductive type.
Okay.
So you can factor out the co-inductive type. That's
oh. So the So I think this, so the dependency only. So the conductive type depends on, yeah, on the inductive. My inductive does not really depend on conductive part. So you can actually construct inductive type first, then use that as. Okay.
Oh, which one?
Yeah, but the portrait is different. So I think what makes
Not the same.
the one I
I think
chose
this one is
more difficult is that they are
copy the
constructed
AV
where
sent
the
to you.
type depends on the.
Someone of the lead for you. You
on
send
the
it to
structure of
AVT?
the contact.
No, it's not my,
Type of constructor.
I'm the organizer.
Oh, okay, okay.
So when-
Maybe someone else sent it. But never mind.
I think that's weird. Yeah. So here, if you do the factoring out of the conductive type from the inductive type, then the Pratt function would depend on itself in the type. Okay. Yeah, but that's.
Use another software to
Open.
open, see whether it can. Because if just to use for presentation, 如果我用 Google 那个什么，叫什么
ordinary dactyl types.
那个对对对。
change it to 用 Google
你的方没有开啊？你的方没有开？而且那个方没有开。一直到我的方，I think this one can close. 你说？
use 宝宝。
each can open. Each. Yeah, can we test the PowerPoint first. We go. 没有聊。Hello. I think just lock in it. No choice, right?
我个人不想，你要想可以想啊，暂时吧。对，啊，这种我都这样。连讲半面色都是。这些的。的。这个也不出用，然后穿。刚才问题这部分。它是 video 的啊？你看的是不是 video？应该是的。它的 font 吗？这些全部都是它的 font 吗？这个不紧，你关掉全部。你来 click 它的 font 算了。click 哦。2分。我做口模修的是挡在前面。Yesterday， 没事，看出来。哦，这个就是放得了。这个就是放得了。这样要一个分。反正第一个算是哪里？这个上面对了。呀，这样就对了吗？我要输出。现在一定要 click 这个。那你是 free 吧？你 free 啦。哇啊，这 GPT 也是啊，结果刚刚都可以了。那一定要带上 video 上。哦，等一下啊，我没去一个 default， 不然只是他们按。对咯，就想到的always 啊。呀。我应该去 S 区。S 区有问题吗？啊，这样不在。OK。做这个你要 test video 呀。啊 ？video 呀。test video 呀。
Today, I will be presenting a formalization of opaque definitions for a dependent type theory. This is work done at Chalmers University of Technology and the University of Gothenburg in Sweden. So to begin with, what is a definition? In ACTA, a definition consists more or less of three parts: a unique name, which is used refer to the definition. The definitions.
Sorry, so I'm just testing video setup.
Correct, Sabra. Third, system call. This is the reason why with
2段とか3段とかになったら何なんだかわかんないじゃないですか。
That's okay. I start video volunteer tried.
Okay, cool. Yeah, so does everything generally make sense, at least? The main problems we had, well, the first problem was actually my fault, and it was just that I had the YouTube stream running on the web browser at the same time as the thing, which meant that we had echoes, so just make sure you don't do that.
So I shouldn't play YouTube streaming here?
Yeah, I mean, there's no reason you should need to play. I basically got the YouTube stream up just to make sure that it was streaming okay.
Okay.
And then, yeah, and then of course
So if I want to check YouTube streaming, then maybe I should just use my laptop.
Yeah, or like do it on here, but just make sure you close it afterwards. Or even just mute the tab, because the problem was that the audio was coming through and then we'd get.
I know.
So the main problem that was an actual problem and not just me being stupid was this. So actually, do you have the timetable up? We do. So I don't know if they're using their own laptops, but basically, I think some of them will be using slides on this machine.
Yeah.
Yes, and I think one of them is going to be a PowerPoint. The issue is that actually, there's a PowerPoint viewer app. Okay, no, this solves the problem. So
It's working?
It actually is working. So I think as long as this app is okay, it doesn't. Okay, so this actually seems okay.
Oh, I didn't know there's play.
I really didn't know that.
Okay, so I remember that you sent a message that you don't have license for PowerPoint. So.
Yeah.
Okay.
So that it seems that just double clicking these PowerPoints opens them up in the player in the viewer. So actually, that's maybe,
what?
Maybe not. Maybe it's got loads of adverts in it. So what on earth is this? That is completely bizarre. Well, I'll tell you what, that's a 20 megabyte PowerPoint as well. So maybe there's just something wrong with it. But we already had that one this morning. So it'd be this one that you're going to be looking at, and hopefully this works. Oh, what is this?
Oh, what?
Maybe when the loading bar gets to the end, it loads properly.
Okay,
no, it doesn't.
What happens if I click this one? Okay, then it's working.
Yeah, absolutely. Okay.
It
seems that up and down rather than left and right is a bit strange.
Yeah, so single of odds.
Oh, what? Okay, no, we can't use this. We can't use this. What? Okay. Yes. Oh yeah. So that's
Yeah, maybe we just present that to just use the computer.
So if they can, then that's much easier.
Yeah.
But they don't have to be able to do that. So for example, one person their laptop stuff run out of battery. So in theory, people are allowed to use this machine. I wonder, is there let's see if the problem is still here. Okay, let me try this thing. Because I do. Hey, well, this is going to work. I'm going to have to remember to sign out at the end.
Yeah, that's
actually, I won't remember because I'm not going to be in here. But if you could sign me out again, that would be great.
Yeah. Of course, I will try to.
Thank you.
Yeah, just I will set alarm.
I mean, no worries if you don't, because I will just probably be able to do it remotely anyway. But
Yeah.
Let's see. Only this app anyway, so that's fine. No one's gonna do it. So, I hope. Right. So in that case, this should work. So, how do I? Right. I actually. Does anyone know how to use Windows? How do I open something in a certain app?
Oh, so that's weird. So usually it shows menu that open with apps. So it's weird that it doesn't show.
Interesting. Can we drag it into the app maybe?
Yeah. That's what I was.
No, apparently not then.
Okay.
I got it.
We can open from here. This PC.
Scroll down, downloads. But it. Well, that's weird. But it is downloads, right?
All files. Okay. So it's compressed. So we need to.
Okay, right, sure, fair enough. And that's why we couldn't change the properties as well, I guess. If we.
Okay, it's just yeah.
There's always something.
Okay, so I think that's why it doesn't show with apps, because it's not Explorer, it's
yeah. Well, I guess I could say that makes sense. I could sort of believe that. So there was another note actually, which was somebody said for TyDe that there's I'll do this after. Okay, perfect. That seems to be good.
Okay, so another one. It's okay. Okay, so it's working great.
That looks great. Suppose you might as well leave that open then just in case. It might as well leave the PowerPoint window open rather than closing it just in case. Sure. Look, okay, fantastic. So the one other thing I wanted to mention is that there was a message saying that 2 talks have been updated. So, so actually, you're going to want to download.
It's already downloading.
Oh, is it?
I believe so. Yeah, actually, yeah.
Oh, sorry.
So you can open this.
Oh, okay, yeah. No worries then. That's fine.
So yeah, so one issue is that there are 2 files with almost same title. So yeah, so
you'll need to ask them which one, I guess, just to make sure. It's probably going to be the larger one. Probably be the M4 one, because otherwise. What? Well.
Yeah, so I don't know why the size is that different. Yeah, I confirmed with. I confirmed and so yeah, he just said so. I can choose the one.
Okay, cool. All right. So MKV they're playing sometime. Oh, you do actually have something we can read. Well.
And that's like all. So I shouldn't play YouTube streaming with sound in this machine and.
Yeah, just
wait, no sound?
Yeah, there is no sound, is there? It is on. Maybe the other one. The MP4 maybe is it better.
Or maybe
okay,
I try will see that has a better codec.
Right, I should get to my room just to make sure everything's okay.
Sure.
But if you have any other questions, then send me a message on Discord.
Of course. Yes, thank you for your.
Yeah,
okay, it's working.
From cool.
All right. Well, good luck.
Yeah.
And bye.
Yeah, good luck too.
Points to learn type-driven programming from text interfaces to a calculus of constraints. I'll begin the discussing what is from. Now, we all
Today, I will be presenting a formalization of opaque definitions for a dependent.
ところで森口先生ってセッションチェアやりますよね。その時のボランティアが僕なのでよろしくお願いします。 そう、だから。
二人を少なくとも動画なんですよね。
あ、そうです。いや、ちょっと、だからそこの森口先生担当のセッションだけ全員リモートで、ちょっと勝手が変わってくると思うので、ちょっと、それでいろいろ確認してたんですけど、ちょっと、なんか、できるだけスムーズになるように頑張るんですけど、トラブル起きちゃったら、ちょっと一緒に頑張りましょう。
どうせ私が、
いやいや、大丈夫だと思いますけど。そこもよくわかんなくて、Q&A にはいるはずで、だからいたら、ズームにちょっとつないでもらうんですけど、それはそう思う。
やっても仕方がないからする。
じゃあ、これでいいかな。タイプドプロンプトは、なぜかファイルが2つあって、謎なんです。画質いい方流してたんですけど。
And object file for a large data set and different structured output. So this is a canonical example of system problem. And this discussion of system prompt is necessary. However, for prompts, kind of system.
どっちでも大丈夫そうです。いや、それ。
LLM is acting as a software component here. Given an input, it generates some output. Now, this is a very credible use of prompts inside a program.
Mic test.あれHello, this is working. Hello, good.
I see the straight.
Oh, what?
Because it is.
Well, why is it that? I don't know.
One camera you are. One camera.
本カメ
自分に映してる未来の風に。
ラ。ああ、そういえば。はいはいはい。そういう機能が。Are you present? Sorry? Are you presenting? Okay. Yes, I'm student volunteer. Yeah, and I'm testing the audio. Hello, hello, hello. Hello? Is it working? Hello, hello. ズームから聞こえてます。あれ、聞こえてます。じゃあ、僕のやつがうまくやってる。So no, I'm not sure if audio is working well, but so he opens the Zoom and he says audio is working.
Yeah, I think there's a microphone there.
Okay, so I don't have to use it.
Yeah, you don't have to use it.
Okay.
There's a method.
And then that's okay.
You can also use this one. Yeah, press this one.
But
yeah.
Hello? Yeah. Hello?
で、2番目の、多分、プレゼンしなくていいと思います。はい。ちなみに、まあ、こっちにも一応パワポがあって、多分できるんですけど、まあ、なんかトラブもし毎日トラブったら、ラップトップに持ってきてもらって、どっちがいいですか？とりあえずもうここのパワポでやります。
その自分のラップトップでやるってなったら、なんだろう。なんかズームにつながないといけない。
そうなんです。とりあえずこれ、撮影できるように確かめたら、まあなんかあんまり心配しなくていい。はい。あれこれですか？はい、そうです。スライドショーで、ですね。プレゼンターなんだ。プレゼンタービューで、プレゼンタービューにすると、録画がちょっとトラブりそうな気が。なるほど。いや、多分それで。 You're talking? Yes, yes. Patrick. Patrick, nice to meet you. Oh, so when are you presenting? 3 o'clock. Okay, okay. So are you presenting in this?
Yeah, if I can just present on that.
You are on computer or? Okay, okay. So you have slides uploaded?
Yeah, just on the internet.
Okay, so which one, so you are presenting constraint generation?
It won't be there, but it's connected to the internet.
Yes.
I could just download them, because I have them up on the website.
Okay,
Which would be.
So could you?
Yeah.
Download it?
Yeah.
Your name? Yeah, so Patrick. Okay, then it should be working. Let's open it just a little bit. Which you want to do?
Whatever, there's no speaker or anything, so.
Yes, yeah,
Anything
anything should be okay. But Adobe Reader doesn't also. What?
It might just be even if you hit that. Dying.
Yeah. Okay, it's okay.
Yes.
Yeah. That's okay. Yeah, perfect. Perfect. Thank you.
Amazing, thank you.
You're a present, right?
Yes.
Nice to meet you.
Nice to meet you.
So I'm student one here, so I think people set up some of these.
Great, cool. Yeah, I'm gonna be using the slide version 2 here. Can I just double click on that?
Yeah, you can just double click. Okay, oh, just a second, I just want to make sure. Okay. Just to confirm, so is it okay to record on the stream?
Yes.
So, okay, cool. That should be okay. So microphone is there, so you can just talk.
Okay. Set a timer for myself. No one, it's not talking.
So it seems I should start sharing the screen. I think I can just. Yeah, I think everything is set up. Quite a student of simulation.
Oh, so wonderful.
Yeah, he does lots of work on Russia.
Yeah.
I'm happy to see you.
Oh, wonderful. Yeah, I'd be happy to talk with you. During the week here. Grab these.
Sure. Yeah, after I'm interested in this topic because so my research topic is data programming.
Ah, okay, wonderful. Yeah, so this will be Korea too.
Yeah. I have some. I know some test of Russia programming. I'm interested in how what's the interaction between them.
Okay, great. Right talk. Guess I'll wait for another 2 minutes.
So welcome to the second session of TyDe. And our first talk will be by Jeremy Seek about gradual method.
All right, thank you very much. Sorry, my students who did most of the work could not be here. As you've maybe heard in the news, things are not great in the United States. They couldn't make it, but it's my pleasure to be here and talk about their work. Well, there we go. All right, so the topic of this talk is pretty sort of, in some sense, quite sort of cut and dry and fairly narrow, which is that we're looking at a certain point in the design space where we're taking a sort of a meta ML-like language that's got quote and splice, or quote and unquote, or quasi-quote, however you want to talk about it. And then we're combining in the notion of gradual typing. Okay? And though in particular for this one, we're looking at a situation where the meta programs are gradually typed and the generated code is statically typed. Okay, and part of this has to do with our collaborators from industry, where you're generating maybe like SQL or something, and you really want to have more guarantees about that generated code. So you want that to be statically typed, but maybe the code that's doing the generation is maybe like Python. And so that's going to be more likely to be gradually typed. Okay, so there hasn't been that much research on mixing gradual typing and this kind of metaprogramming. Actually, concurrent to the work that we were doing here, there's a paper in GPCE this year that also is sort of first steps. And I'm gonna say just a few words comparing what we did to what they did. A lot of it's very, very similar, and there's just sort of one little design decision that's different. And so, yeah, the whole point here is to talk about like, well, how do we deal with the interaction between gradual typing and metaprogramming? How do we put the two together? Okay, and just to kind of give a high level overview of like the different artifacts in this system that we're building, is you've got your source language where you write your metaprograms, and that's this meta GTLC. And then the semantics of that, as usual, we compile down to a lower level language. Down at this level, this is CC is for cast calculus. So this language has lots of implicit conversions because it's gradually typed and there's lots of dynamic, sort of implicit dynamic checking happening. Down here, it's all very explicit. And then you run your meta program, and that's going to generate essentially simply typed lambda calculus. And then you can run and then this is completely standard running the generated code. Okay, so that's kind of that's the setup. So just diving in here, the syntax of this meta GTLC. First off, we have the types of the meta language. You've got your base types, you've got function types, so that's the usual. Stuff that's just black is like STLC stuff, okay? The blue things are going to be your typical things you get from MetaML, okay? Your typical meta programming features. So this is like this is a code type here. And then the star here, that's the any type from gradual typing or the unknown type. And this is saying you don't know at compile time what type the thing is actually.
So what's this thing on the left that looks like an eye without a dot?
Oh, that's your just base types like that and bool. It's ranging over that. So now what's a little bit interesting here with the types of the object code. So here we have our STLC types. This is just, you've just got functions and base types. And so what you have for your code, well, it's got just STLC stuff in there. So you're not going to have mixtures of the star all over the place. Instead, you can only have it sort of at the top level. So we're really sort of in the meta system, we want to be able to say you have code of unknown type. And you can say that with this grammar, but you can't say I have code of function type that takes star to something, right? Because this is the STLC inside of our code, right? So it's statically typed there. Okay, so then our meta programs, you've got your usual lambda calculus plus quote. And then for your object code, you've got lambda calculus plus splice. So that's just the usual thing. Here we've got type annotation, and that's hinting that we're going to be doing a bidirectional type system. And we were sort of forced into that for a very technical reason that I'll get into, okay? We didn't start out saying we were going to do bidirectional, but we sort of ended up there. Okay, so we're basically just marrying, the stuff you need for metaprogramming with the stuff you need for gradual typing. Okay, now one point I should make about this language setup here is that this is super simple. Okay, this is like we're taking first baby steps towards integrating gradual and metaprogramming. We've left out eval, and we've left out things like mutable references. And so with this little language, you don't have to worry about this thorny problem called scope exclusion. Okay, so that just can't happen in this little language. Okay, we're currently working on what happens if you do add those things, and then things get a lot more complicated and a lot more fun. Okay, so like I said, so this was our sort of our source language, and then we're gonna compile this down to this cast calculus. Okay, and this is the cast calculus is sort of where we're really going to be like spending our time, like really thinking about the runtime semantics, okay, what's happening. And in this language, you now express all your implicit casts explicitly, okay, with this is a term M with a cast on it. Casts are explained through this sort of combinator language called coercions. This is a really nice little language that Hengline developed back in the 90s. And it turns out that when you're trying to design new gradually typed things, it's really helpful to
do it using coercions because they sort of like give you less freedom and sort of steer you towards the right thing. Okay. And so the red stuff is all standard, coercion calculus stuff. But then the green stuff is the new stuff you need for the interactions between gradual typing and metaprogramming. And so what we have here is it's a cast on that's under a quote. Okay. So actually, let me show you the typing rule for that. It's this one right here. Okay. So if you're trying to cast from one quoted type to, one code type to another code type, you can do that, and as long as you can cast from whatever the underlying type is. Okay. And it wasn't hard for us to come up with this rule here because it's a lot like the function rule, except it's easier, right? With the, if you just look at the domain here, how you cast the return value of a function, that's what that's doing. And you don't even have to worry about the contravariance over here. So this is pretty simple to come up with. There wasn't a lot of freedom there. So these coercions, so this is Henglin's reduction system for this little combinator language. Okay. So for example, if you have an identity coercion, then that just goes away, right? It's identity. If you have, so these bangs and question marks, the bangs are injections. So you're going from some type to the unknown type. And then the question marks are projections. So you're going from the unknown type to like integer, okay? And the question mark ones are the ones that could fail at runtime. You should think of those as like procedure, or things like that in bracket. Like you're saying, are you a function or are you a number? And the L there is the blame label. So it's like, if this projection fails, you want to give an error message and you're gonna be able to like point back to some line number in your program that's being stored in that information, right? So like this is a check that succeeds. This is a check that fails, if A and B are not equal. Okay. And so the cool thing, one of the cool things here is that most of this is just read like standard coercion calculus stuff. We didn't have to make very many changes. We just basically had to say, how do you deal with this quoted coercion? Okay. And this first rule here is a distributivity rule. Just says, how does quote distribute with sequencing? And it's just, you just push it inside, right? Which is quite similar to what we do for function types already. So that didn't require that much thought either. And then this one, this is oftentimes you have got these rules for bubbling up identity, that you're discovering that you've got an identity cast. And you start like, here's the one for functions. If you have a function cast that's not doing anything to the input or the output, that's just an identity. And same for, so we just had to do the same thing for quoted types. So that was easy. And then once you've done that work for the coercions, then here's the actual reduction rules for the actual lambda this lambda calculus with casts and coercion. Okay. And the cool thing here, again, is that most of this stuff is just standard that had nothing to do with the intersection of the meta and the gradual. So this is all your just standard gradual, what you need from a coercion calculus in terms of reduction rules. And then, these are your standard reduction rules for splice and quote. Of course, you need to be able to reduce under quote to get to your splices. And if you've got a splice, you need to reduce under that, reduce whatever meta stuff needs to happen under splice. And then finally, you've got splice quote. That just, they cancel out. Okay? So that's all standard. The only thing we had to add was just that what happens if you have a cast failure in some meta program that's inside of a splice, right? And obviously you want to propagate that exception up to the top, right? And so we just had this rule for propagating our exceptions up through splices and quotes. One thing I'm not showing you here is there's a lot more like congruence rule kind of stuff that I'm not showing.
So. All right, so I want to do, here's where we want to do sort of this, there's like this one design decision about what's going on differently in our paper versus the Uchi has come up Miala paper in Gypsy 2005. So their reduction rule for what happens when you coerce, when you have a coercion on a quote, is they push the coercion into, through the quote. Okay. And so this reduction rule follows the traditional pattern that you'd see for other things in terms of other kind of introduction forms like lambda. So like one of the way, like when you cast a lambda, you apply a function cast to a lambda, you could do like an eta expansion of your lambda and do, and inside of that, you're going to be casting the domain and codomain. So this is a similar kind of thing like that. We're sort of pushing this coercion underneath. However, what this does, this rule does, it's basically saying we've got a cast that was happening at during meta evaluation. I mean, when you push it under the quote, it's now going to delay the cast to maybe fail, but not at meta evaluation time, but at the runtime of your code that you're generating. Okay. And so that's something we didn't want to do that delay. And we want to have our errors, like if we have a cast error, we want to know about it during meta evaluation and not during when we run the generated code. So that's why we steered away from that rule. Also, this reduction rule sort of assumes that your object language that you're dealing with inside here is gradually typed, that you can have casts in that language. But if you recall, our object language is the STLC. So you can't have casts in there, okay? And so it doesn't really make sense to have a cast showing up inside of a quoted term. Okay, so that's another reason why we sort of ended up with a different design. And so maybe it's a little bit hard to see like why, like where's the lack of this rule over here? So like, let's say like one of these V's could have been like a quoted entity, right? A piece of code. And you'll see there's no reduction rule. There's no one specific to that. Like we don't have this actual reduction rule in our system, right? But what's happening instead? You could, like this C here could be like a quoted, coercion with more coercions inside of it, right? And so here we're saying, oh, do coercion reductions inside of there, okay? And then, that's going to trigger the stuff from this page, right? So maybe you have, stuff like that going on where you're composing those and so on, okay? And maybe your casts on your quote go to ID and then, then they just go away. Or maybe they trigger, blame, okay? And then the blame gets propagated up, okay? So all of that kind of stuff can happen either through here, and then it finally turns into an ID, and then it just goes away, or it goes to blame gets propagated up, and then your whole program goes to an exception. So we basically just never, that those casts involving quotes either always turn into IDs or they always turn into blame. It's sort of the at the end of the day. So that's kind of the story there. Okay, so we've now established the source language and then the cast calculus. And then now the question is like, well, how do we compile the one to the other? Okay. And this compilation is type directed. So here we're sort of seeing both the type system of the source language. So this is the gradual type system, and we're also seeing how do you compile down to the cast calculus. Okay, so there's sort of two things going on.
Again, the things in black are just your normal, what you'd expect to see if you're just STLC. And then the red things are standard for gradual typing. So like how you compile function application is just completely standard. And then like how you compile quote, this is going to be completely standard. So now we're going to get into this one other sort of main point of this talk, which is why did we do bidirectional? Okay, and you'll notice that. So for this compilation here is for the meta program, the meta level, okay, which we're not doing bidirectional here, okay, but we are going to do bidirectional for the objects. So once you're inside of a quote and you're compiling that code, that's going to be bidirectional, okay. And so the reason is over here in green, okay, which is that we're looking at a splice here, okay, and and let's say, and we can compile that the meta code, the meta program, to M prime has type A, and then that type A could be something like dynamic, like the unknown type. That type A could be something like code of dynamic, okay, code of unknown. Whereas the context here is STLC, so it's got to be a fully static type. Okay, so it's likely that we're going to need to do a cast at the boundary here between our gradually typed world and our statically typed world. Okay, and the fact that we've got this consistency check here, like, okay, that's the implicit check that would be happening in the type system. And then for the runtime, we're going to need to generate an actual coercion that'll do the runtime work of that cast. Okay, and this cast needs to live in the meta program inside the splice, right? We can't do the cast in the object code, that stuff's statically typed. So we're going to need it inside of the meta code here. To figure out this cast, we need to know the target type of what we're casting to, okay? That target type of where we're casting to is whatever's the static type expected in the context of the splice. So we need to know, like, above the splice, in the AST, like what the code above us, that STLC code above us, what is it expecting, okay? And so this means we need to be doing bidirectional in checking mode. Okay, so we get the target type T from being in checking mode. Okay, so that's why we had to go bidirectional. We sort of got to this splice rule. We're like, how on earth do we insert this cast? We need T. Okay, fine. We'll go bidirectional with that. Okay, so that's one of the other main points is that rule there. Yeah, if we didn't go bidirectional, I wouldn't know how to do this. I mean, maybe there's other ways to do it, but this is what worked for us. Okay, so this is now going into the, how do you generate those coercions, right? The coercion calculus. And so almost all of this stuff is completely standard. And this is like, oh, if you're going from some type to star, that's a injection. If you're going from star to some other type, that's a projection. Okay, so that's all normal stuff. We mostly just needed to add rules for dealing with quoted, if you're casting between quoted types. Okay, and that's where this quoted coercion comes in. Okay. This was pretty straightforward to deal with. Okay, so does this design deliver on what we're hoping for? The basic thing we were hoping for is type safety. And so what this says is, okay, you've got a meta program that says, I've got type quote of, code type of type A. And if I do a compilation and compile that down to N, so this is going to be in our cast calculus intermediate language. Then, as usual, we've got three options. It either can run, and then we're going to produce code of the expected type. Oops. T. Oh, you know what? This T should have been, actually, this A should have been a T. I'm sorry. And then, or you might get an exception, like you've got this is gradual typing, so just like dynamically typed languages, sometimes you can throw exceptions, and then you might also have divergence as a possibility. And so that's kind of the usual type safety proof that you'd expect. We did formalize all this in AGDA, and the proof of type safety is in AGDA. Okay, so to conclude, metaprogramming and gradual typing can be integrated. And the main thing you want to do is add a quote coercion. Okay? So the other main point is this thing about, at that splice, at that point where you need to do the splice, you may very well need to add a cast at the place where you're doing a splice. And that's why we needed the bidirectional typing, so we know where does that cast go into, to make sure that we could put the cast in the meta part of the program. Okay? And if you'd like to look at this in more depth, here's a link to the GitHub repo where we have all the AGDA code for that. All right, so with that, stop just a couple minutes early here. Plenty of time for questions. Yeah.
Can you let me say that bidirectional typing is a limitation or is bad? Like what was the problem?
I wouldn't, nowadays I like bidirectional typing, and I would like if I'm gonna go design a new language, I would make it bidirectional anyways. But that's my opinion. Like there's probably a lot of other people who'd be like, no, I want something else. So that's, I'm just, if you said, oh, I want to do Hindley-Milner, I'm not sure how I would do that for this system. And maybe that's a paper being, that needs to be written as how to do that. So yeah, it kind of depends on your perspective, I suppose.
Before the next question, let's thank the speaker.
So you said that this is like the standard way of doing this kind of rule where you put the conversions in there. So these are where it's like this previous standard rule of to drop it sort of inside of the quotation, so you have it in the next stage.
Yeah. Okay.
And then you have this alternate way of doing it that lets you catch it earlier.
Right.
That on the face of it, that sounds strictly better.
Yeah.
Is there some advantage to the older way of working it? Why would I prefer this over the way you said it?
So actually, this isn't older per se. This is concurrent. So this is we actually, in fact, we didn't know about each other until we noticed each other's publications coming out. We're like, oh, hey, and so, but this rule is the kind of I don't know. I should ask Higuchi how he came up with the rule. I don't literally know how he came up with that rule, but this rule looks like a lot of the rules that you would see for Lambda, or for other introduction for pairs. How would you push a coercion through a pair? It would look like this.
It's pragmatically, resulting language, catching errors earlier. It seems better to catch.
Yeah, absolutely. So I don't know how much they thought about this trade-off. Maybe they didn't think about it, or maybe they did. I don't know. But to me, this was almost like a deal breaker, where it's no, we don't want to do that.
And then another kind of sort of somewhat related question. So you were saying in the type safety proof, what are we doing to happen?
Yeah.
But there's one, isn't there maybe it's captured in the term, but the case of there isn't enough type information in the meta program to get a fully typed final, if you're going down to a fully typed language, you can imagine it's you can have any type applications anywhere, and you can't get it. So is that divergence? What's that?
No, we've sort of set things up static in terms of we've set things up sort of syntactically and whatnot, where the quoted stuff has enough annotations and things on it that it'll definitely be fully checked. And I didn't even write I didn't say anything about running this code, but this code here
is STLC, so you just use the normal STLC type safety group to know that you will not get any errors whatsoever. Like you won't even see blame kind of errors. This one will either go to something of type T or it'll diverge.
That, like, in the like real world, not thinking of, applying this to, like, someone like tracking together something in Python that's gonna like evaluate down to something that's got to be that language.
Yeah.
Does the error case I'm talking about exist there? Where like, they just didn't, it's a graduate hit system, they just didn't write enough down to know.
Knowing that setting too, it's that our type checker, our gradual type checker is like being fully static about the quoted bits. So it's like catching a bunch of errors really statically there. Ron. Uh-huh. Yes, that's wonderfully said. Yeah, because whenever any actual coded term you have is going to have its type, like if you're thinking like canonical forms or something, its type is going to be quote of like int or quote of like int arrow int. It's going to be a fully static type. But that quoted thing could be flowing around in this gradual meta program, getting passed to a function that was expecting something of quote star. So you lose that information as it's passing around, but then maybe later on it's passed to something that says I'm expecting quote of int, and you've got a projection happening there. I think as soon as you make that step, I think you're sort of like saying, I want gradual typing in my object code. Okay, I mean, if you maybe like writing some example, we could look at some examples of what you have in mind, and then that would become clear. And like, I mean, because the main thing you do with code is you splice it into other code, right? And at the moment when you splice, we're going to make sure that it's like fully statically matching up. Exactly. That basically got a question.
The only things you can do with the star,
yeah,
that's all.
Yeah.
And if there's more precise type inside, to see what.
And the way we're doing the coercions and stuff in the compilation is that as you're doing that splice, the actual type of the thing being spliced has to be fully static again. So maybe you have some projections happening right there that are getting you back to fully static.
I was thinking like your 3 segments, you got a program that like I don't need to do what the place of the person I really need to participate in.
Oh, okay.
So
yeah, I think
should take the rest offline.
Yeah.
Sorry.
Yeah,
Okay.
I'm digging what you're saying. I get it. Yeah.
Let's thank the speaker again. So
Sure.
これ、どうやってスライド切り替えればいいですか？
アローキーで、アローキーに、はい。
okay. So our next talk will be by Satoshi Takimoto about unification modular isomorphism.
Yes, so hi, I'm Satoshi Takimoto from Institute of Science, Tokyo. Today, I will talk about unification modular isomorphism between dependent types for type-based library search. So let's start with the motivation. So when we develop software, we usually rely on reusable software components like functions provided by libraries, because in order to speed up development, right? And library search enhances such code reuse by helping users find such components, and it's therefore, yes, library search accelerates software development. And this capability is crucial for important in ITP, interactive frame provers, as proving things is difficult and time consuming. So so reusing lemmas can make a huge difference. Type-based library search is one promising search method. So it allows search by types. So you give a type, then it will return functions and such whose types match with the query. So, and one real-world example is Google for Haskell. I think you know Google, or do you use Google? Yes. And in the context of ITPs, via the Curry-Howard correspondence, type-based library search enables search by proposition, which is really nice. Okay, useful search flexibilities. So the simplest implementation of a useful search flexibilities, simplest implementation of a type-based library search would be just comparing types, right? But that's too restrictive and too rigid, often too rigid. And I think here's a list of the search flexibilities that I think important. First, the reordering and currying. The difference in the order of arguments and components and size of equalities is very superficial, and also the difference in whether functions are carried or not is also superficial. So we would like our search system to ignore such differences. So we would like the tool to identify these two types. And next, definition unfolding. Users may not be aware of all the definition in libraries, right? For example, I use Agda myself, and its standard library got this commutative and this type alias for commutative statement. But if we don't know this alias exists, we might query with this type alias inline, right? So, but so we would like our search tool to ignore this difference and consider two types equivalent. And generalization, this is also important because libraries may provide definitions that are more general than what users give. So, so for example, here we got the type for natural number recursor, and this should yield the eliminate should also yield the eliminator because it's more general. And the final extra premises, users may not notice that they need additional premises to derive certain conclusion. For example, suppose we want this m minus n plus n is equal to n. But if the subtraction is defined to truncate at 0, then we actually need additional proof that n is less or equal than this proof. But So it would be nice if our search tool can automatically complete that additional premise. Yes, existing, yes, several different search tool, type-based library search tool have been implemented. So we have Lugu for Lean and LambdaPy and Idris has its own type-based library search command. And we also had search ISOs for the work group in the past. And yes, they target different search skill. So some are global, meaning that they can search through the whole ecosystem or a huge library, while like Idris, it only search is within a few specified modules. And partly because of the search skill, these type-based search tool comes with different search flexibilities. Like some supports carrying while others don't. But none of all supports all the flexibilities simultaneously. Yes, and our work aims to realize highly flexible type-based library search that, yes, that supports all the flexibilities we've seen all at once. Because of the trade-off, it will our method will be more suitable for local search currently, but yeah, we'll pursue more scalable search in the future. And we realize that search tool by unification modulo a specific set of type isomorphism. We will see soon which specific isomorphism, but the unification part handles generalization and extra premises. And the isomorphism part captures reordering and anchoring such. For example, if we have this constraint, on the right we got the type of natural number eliminator instantiated with some meta variable n. And on the right, we got an unusual type signature for natural number reconstruct. So in unification module isomorphism, our goal is to find a unifier or meta substitution for meta variable that make these two types isomorphic. And in this example, this substitution indeed made two type isomorphic. Right. Okay. The idea of using unification or module isomorphism is not new. It's in fact from 90s. So we have unification module isomorphism between Hindley Milner. This is by Ritchie. And we also have comparison, not unification, module isomorphism between dependent types. And this is what search ISOs adopt. And so basically we are parsing the combination of these two functionality wise, but combining these algorithms is hard because Ritchie's algorithm does not extend to dependent types. So our contributions are these two: our unification procedure, modulo isomorphism, and our prototype search tool. We also provide prototype search tool implementing the procedure. Okay, next, let's see the isomorphism we adopt. So it's a standard isomorphism involving function types, dependent function types, dependent pairs, and identity types. And this is what, this is similar to what search ISOs, the research by Dylan Hyatt. But it's actually a dependent counterparty of dependent counter part of what we treat adapt. So the simplest isomorphism is this. Two types are isomorphic if they are beta, eta, delta convertible. By including delta conversion, we handle definition unfolding. Next, the promised reordering isomorphism and the carrying isomorphism. So we have reordering for function type, pair type, and the equality, the identity type. But because we are dealing with dependent types, we need to be careful about the dependencies between components and domains. Here are other useful isomorphisms. So we have this associative isomorphism for dependent pairs, and we also have 3 unique eliminating isomorphism. Okay, now let's see how our unification procedure works by example. So our procedure operates on a set of constraints, which is essentially a pair of terms in context. And each unification rule transforms a set of constraints into another. And here we take this constraint from the earlier slide, the type of natural number eliminator and the unusual natural number reconsider type. Okay, here we clarify the type of the function element. Like this, in order to handle search modulo unfolding and carrying, we have the rule normalize. So yes, first, so we normalize type saying constraint using a React system. And next, decomposition. So like standard unification procedure, our procedure decompose a constraint into a set of smaller, simpler constraints. But we need to do a bit more work because we want to handle reorder. So our decomposition rule can reorder. Like in this example, notice that the second argument of the left is now equated with the first argument. And in this step, yes?
Which isn't A instantiated?
Sorry?
Is A instantiated for M applied to 0? And if so, why only some things? I'm trying to see what happens in that step.
Okay.
so many things change, so it was a bit unclear.
Okay, so yeah, it was, sorry. So we, we decompose this constraint into what we are trying to do is to decompose this constraint into smaller constraints. So in standard unification, we would decompose this constraint into this and this, the first arguments, and then the rest. But here we reorder these two arguments, then decompose. That's why we get these two constraints.
Yeah, but then M0 is automatically A, but A is used to several places. The second argument on the right-hand side of the comparison is A.
Oh, yes. So here, right? This A is from this, and this is from this. Sorry. Okay. And next, in this step, we apply reordering decomposition again, but this, unlike the previous step, we do a pruning, so-called pruning. That means because we are dealing with dependent types, sometimes such dependencies between components and arguments may block reordering. And to proceed, we sometimes need to prune meta-variable arguments. Like in this example, we substitute n with a lambda that just returns a fresh meta-variable n prime. And that way we erase the dependence between these arguments, and then we can compose. And solving for meta-variable is done like a standard unification procedure. And now we have a constraint that can be solvable and done. Yes, so a procedure. This is the flow basic. This is the flow of our unification procedure basically. So we first normalize types in each constraint, and next simplify constraints by decomposing into smaller constraints, and sometimes reorder. Actually, we do that reorder non-deterministically. And unfortunately, that was not covered in the example, but we also partially guess meta-variable in the simplification step. And also, we also choose non-deterministic if multiple simplification ways. And next, we solve meta-variables in constraint that can be simplified further, and repeat these 3 steps. Okay, let's see each rule in detail. So in normalize, we fully reduce terms in each constraint with the React system we call R. And here's the one-step rules for R. So this is basically what we can obtain by orienting the isomorphism, the chosen isomorphism, excluding the reordering isomorphism. So what we do here is, by this rule, is unfold definition to and clarify function types, and make dependent pair types more right nested, and eliminates the unit type. And decomposition. So decomposition. So during decomposition, reorder non-deterministically to handle reordering isomorphisms. And for identity types, we just swap size of identities. And for function types and pair types, we choose one of the arguments or components non-deterministically, and bring it into the front. So for example, suppose we have this constraint, we have iterated function type on the left. So we decompose the constraint like this. This is like a standard unification procedure. So we don't reorder. But non-deterministically, we try this. So we bring the second argument to the front and then decompose. So that's why we get A2 here. But because because of the dependencies, we have dependencies here. No. We are dealing with dependent types, so we need to be careful about the dependency. So, and the arguments to meta variable may block reordering. Like if we have suppose we have that constraint, and the second argument y, the type of y depends on the first argument x, right? Mx is, so m is meta variable, and the type of y is m applied to x. And to proceed further, we can proceed further by proving the arguments. So what we do basically is to we first compute the minimal set of meta variable arguments to eliminate, and then actually and then this substitution, and and in this case we can by pruning we can actually find a solution. But pruning is not always possible in general. For example, like this, if meta variable, no. So this second argument depends on the first argument, right? And k is applied to a meta variable m. But since we have this k here also, we cannot erase this dependency. The pruning can't help here. Yes, and the guess meta variable rule, which was not in the example. So during unification, we can sometimes infer the structure of meta variable actually, like from if we have a term, if we have meta variable applied to some term, we can it is a valid guess that m is a lambda abstraction, like that abstraction, right? And there are more valid guesses when considering isomorphisms. So from suppose we have that suppose we have a dependent function type whose domain is a meta variable, then we can guess that m is either unit or a dependent pair. Oh, it's tiny, right?
Let's say 2 minutes.
2 minutes? Okay. So this creates the new regex in the sense of R, and that is going to be reduced by the following normalization rule, like hereditary substitution. And likewise, if we have this, so I'm going to skip some. So in general, we guess meta variables that are function domain or domain or pair components. And sometimes such guesses are unhelpful. Okay, I think I don't have time, but so to prevent such an helpful guess, we sometimes impose suitable conditions on each case. Yes, and based on this, we implemented a prototype search tool. It's naive in some parts, but we in the implementation we made definition unfolding lazy, and the search system completes search quickly for tiny library set, like in this small library sets and library set, and this is available on GitHub. So in conclusion, I presented a unification procedure for highly flexible type-based library search in ITPs with dependent types.
and by taking type of isomorphism into account during unification. And future work, yes. First, make unification, our unification procedure isomorphism producing, because we only produce unifier, but not isomorphism during used during the unification, and that that evidence will be useful, for example, for code generation. And support for covers why do we use the language features and provide the theoretical foundation, and also achieve more scalable search via time indexing.
Let's thank the speaker.
Just curious if you sort of tried running it on the bigger example to see, I mean, theoretical scaling is one thing, but in practice, I mean, if you, if you include a 200, because there's lots of code in the IRL libraries.
Yes.
Is it awful or is it sort of just bad? Scaling.
Scaling. I think it's. I'm not really sure, but it's the time will grow exponentially for large type, because our procedure is highly non-deterministic. So we try many branches during unification. So yeah, we are trying to make our procedure more deterministic. But yeah, we'll do a performance evaluation with with a larger data set in the future, and yeah.
Yeah, I mean, so for example, have you tried any of the examples you had in the motivation slide with addition, commutativity, for example?
Yes, and that completes quickly, actually.
Okay, but then you just have like commutativity, addition. You have just a few definitions.
Yes, we only had like a 38 definition. So yeah.
I don't think the problem is big types. The problem is a big library to search.
Yeah. Yeah. True. Oh.
Great to see where it's not.
Thank you. Sorry.
Are you presenting any kind of cycles in reordering or anything like that? Basic branches?
Oh, sorry, I can't still catch. Sorry.
What? For even reorder?
Yeah.
Like how are you presenting basic cycles? Right now. Is there anything before you?
Our procedure it prevents okay. That is by only doing reordering by decompletion. Okay. Yes. That's how we do it.
Okay, let's thank the speaker again.
Yeah.
So the last talk of the session is by Patrick Ferry. It's about generating Hazel.
Thank you very much, and thank you everyone for coming. I realize this is post-lunch and at the end of the session, so just hang in there. It won't be too as technical as the other talk, so hopefully that'll help. But yeah, I'm here to talk about generating Hazel programs from ill-typed camel programs. This is work that was done with Anil Madhavpedi and also Max Carl, and I'll talk more about his work during the presentation. But the problem that we kind of faced with here is that new languages that are being developed don't come with a large set of programs already written in that language. And there's lots of different reasons why you might want to have a large set of programs already written in that language. And the main one for us was that we were doing kind of research in error handling or error messages in the Hazel programming language, but didn't have enough ill-typed programs to do any kind of evaluation for some work that we were doing. And language designers are constantly juggling many different requirements when they're building a new programming language. And this is going to vary depending on, is it a new language or is it decades old? Are you handling backwards compatibility? Do you have some kind of embedded foreign function interface in there? Are you kind of catering more towards pedagogy, or are you trying to do an industrial strength language? All these sorts of things. And kind of one thing that is true for all of these is that you probably want to have some purposive programs that are both correct and incorrect in your language to be able to make sure that you're trying to hit some of these different aspects. So one way that you can maybe get around this that doesn't require finding a lot of people to write lots of programs is kind of making use of other more mature languages that share some kind of design or lineage with your new one. And most likely there's one there somewhere. This is one example of something that you could use to try and find those languages. And this kind of divides up a good set of languages based on the different paradigms. And if you go and take a look at this diagram later, you can see that these languages also appear in different parts of this graph. They're not just constrained to one little section. As I mentioned at the start of the talk, we were focusing on Hazel, which is a ML style language. And we'll get on to some of the features of that language. And so we wanted to focus in on that section of this diagram. And OCaml was very well suited to being that language that we could perhaps use to generate some programs for Hazel from. And kind of the reason for that is that, as I said, Hazel itself is quite ML-like, although it is gradual. It's interesting in the sense, one of the interesting features of the language is that the editor is co-designed with the language itself. So if you go to hazel.org, you can have a play around with that language in your browser. And because there are these things called typed holes in Hazel, incomplete programs are completely unallowed. And in fact, these programs might not type check or might have an ill type, but they can still evaluate in Hazel, which for me, doing a lot of teaching in programming languages, is certainly an interesting feature to have students be able to play around. So just to do a little side-by-side comparison, Hazel is very like OCaml when you're doing some kind of just pure subset of OCaml. There's some syntactic changes between the left and the right, but other than that, there's not too many differences. Some things to note are that type annotations are quite a lot more useful in Hazel, given that it doesn't have the same inference that OCaml does, which we can see here in the sum function. But other than that, for the basic cases, a lot of it is syntactic. As I mentioned, Hazel comes with typed holes. This is kind of its unique selling point as a language, I would say, which allows you to insert these holes here shown in a question mark in ASCII, but in the online editor, it's kind of all built in and looks nicer. And you're allowed to evaluate your program across those holes. And it'll use some kind of gradual type system in there to be able to cast some of these dynamic values later on, and then tell you, actually, if you're going to fill in this hole, it better be an integer because that's what I think it should be. And so you can see here, for example, with the length function, we don't actually use any of the values actually in the lists, and so we're able to evaluate that all the way to the number 4. And then using the sum function is kind of the opposite. We are interested in the values that are stored in the list. And when we go in and look at them, we actually come across a hole. And so we can't evaluate the program all the way to a value without holes, but we can go a long way. And the colon int is the cast. And so the cast is a good point to bring up here because the work that we were actually trying to do this all for It's being presented at Hatra on Tuesday by Max Carroll. And what he was looking at, and I was supervising him on, was decomposable type highlighting. And again, this is kind of for one part for pedagogy, but another part for just understanding errors better in functional programming languages. And so we have a really simple example here of an add function that takes X, Y, and adds them together, and then immediately we supply it with a string. And then Hazel, this kind of gets shown to the user at this point in the evaluation as a cast that's gone wrong. But before Max did his work, it didn't actually tell you why it's gone wrong or what parts of the program are contributing to the fact that this cast exists in the first place. And this is often, at least in my experience and in others, quite a hard thing sometimes to teach to people who are doing functional programming for the first time. And this is steps in the right direction, I think, for having a better integrated experience in the editor and in the language itself, being able to explain a little bit better why the program's gone wrong, and hopefully then how you can go about fixing it. Another reason that OCaml was a pretty good language to do this for, or use it as the source language for this, is that there's plenty of programs like there to be used, both in terms of kind of, programs that we might want to translate. For example, the standard library, we might get a almost for free standard library in Hazel just by converting it straight over. There's plenty of published packages, there's research tools, and the test suite itself in OCaml is pretty extensive. But on top of that, there's also work done for a very similar kind of project that took novice interactions with OCaml from undergraduates and produced a corpus of programs from that is really well kind of segmented into kind of like ill-type programs and not ill-type programs, alongside actually keystroke by keystroke kind of traces of students writing the OCaml programs, which seems to be a great resource, but we can't really use in Hazel because it's not written in Hazel. And so we were hoping that we could just take this entire corpus, translate it over, and then run some analysis of the type highlighting on that set of data. And so we built this tool that's Hazel OCaml, and it takes OCaml programs and translates them over into Hazel. And as I mentioned before, much of that is just a transformation of syntax, which is great. There are some syntactic changes that don't mean a lot. For example, in pattern matching, the arrow gets an equals instead of a hyphen. But there's also some work to be done in terms of desugaring some things that are in OCaml. Hazel being a research language is still fairly close to kind of the theory of a lot of programming languages. It doesn't have a lot of nice bells and whistles for developers like disjunctive pattern matching, but a lot of these can be desugared out of the way and then mapped over. One thing that is definitely a bit of a pain is that there's no module system in Hazel yet. There are branches that implement it, but anytime we come across something that's making use of the OCaml module system, we have to make a decision of whether we're going to do some kind of just renaming to some kind of top level function that we can then bring over into our Hazel program, or we might just decide to give up and say, actually, things that use some set of modules, we're not going to do it all. And things that come to mind for that, or anytime we might get involved with like a functor in OCaml, at this point, Hazel perhaps doesn't have enough to be able to encode that in a useful way. And so we might just stick to things like list.map becoming some kind of name munging between list.map and a top level function. One really nice thing that came out of doing this project was that having typed holes in your target language is really useful, because at any point you can insert a hole when you haven't decided how you're going to translate something across. That could be for things that you just don't support, or it could be for, when you start initially writing this project and you don't have all of the different expressions in OCaml translated, you can still put an empty hole in there and you get out the other side a Hazel program that you can put straight into the editor, have a play around with, and make sure that you're building it properly in the first place. And it can also just be for kind of parts of the language that you don't intend to map over, and you can still compile it over and put it into the editor and get some useful feedback, which is pretty neat. And one last thing is that we were able to kind of bring directly over OCaml's type checking into Hazel, where polymorphism is completely explicit, which is a lot of pain to remove from, say, writing a standard library of list functions or something like that. And if I show the actual Hazel program, you can see it gets a lot more syntactically heavy. And there are again branches, but they haven't been merged in Hazel for doing some implicit polymorphism. But so far they haven't been merged, and so it's nice to be able to make all this boilerplate easy to do by just bringing it over from OCaml. And the reason why it's fairly straightforward to do as well is that the system of OCaml tooling is pretty good for asking about types. So for example, with OCaml's Merlin library and tool, it made it much easier to just ask what different types there are in the functions and be able to map that across into Hazel and then do the type abstraction and type application for the user directly. I think it's also, again, to bring it back to like a pedagogical point of view, it's a nice way of teaching some of these things to people where we do a lot at Cambridge, we do a lot of OCaml programming in the first year, and a lot of the things are kind of happening for them under the hood, and you have to explain to them kind of how these things are actually happening. And something like this might be quite useful for that, and having some kind of translation between these things, I think, is of kind of practical use in that setting. So some of the use cases from the actual ill-typed code, this is an example just from the data set of someone writing a summing function over a list. And there's a few kind of classic errors here that I think novice programmers make. So in the first one, well, first of all, the pattern matching is not exhaustive. There's nothing for the singleton list. Also, the empty list should probably go to 0. That's probably what they want. And then with OCaml, that mistake in the first pattern match is going to affect the type errors that they're going to get when they come to the second branch, which is now trying to return an integer, which is what they want. But it's not a list, which is what it expects. And then within the brackets, we've got probably just some confusion happening with what it is that they're trying to achieve and the ordering of things. And so this converts just fine over into Hazel. And we have an option for both trying to do that type checking and bring OCaml's type over into Hazel, and one for not. And the reason for that, again, is to, as we're not, we're making a trade-off here with time and effort. It would be great to have a really extensive amount of programs written by students for Hazel, but we don't have that. And so we're trying to mimic at least some of the kinds of mistakes or the kinds of errors that novice programmers might make. And so I think one of those is definitely when you're writing Hazel, you might just not type annotate at all. You just go straight for a function, for an implementation. And there's different errors that we're analyzing here. On the right, we've just got, Hazel's kind of dynamic types. There's kind of nothing wrong with this, except that it's not exhaustive. And then on the left, we have more type information, much like the OCaml case, except due to Hazel's type system being slightly different, and the error messages being slightly different, we get what I think is perhaps a better error message for the difference in the branches, which is to say that the type error here will say that there's an inconsistency between the branches, which is maybe a better way of suggesting to check all of your branches and make sure they're returning the right type instead of more authoritative kind of the 7 branches with the wrong type. And then here's an example going one step further for the decomposable type highlighting, where we've got a fairly common mistake of using a cons operation instead of an append when trying to write some kind of concatenation function for lists. And the point here, there's a few things that we can know. One of them is that Hazel evaluates this just fine, so types are not right. And what we can then do is inspect the cast of the integer and the type highlighting tells us where that class is coming from. And it's coming in part from this cons, but also from the fact that we've annotated the function itself to return an integer of lists. Being able to explain that in a way where you can show, I think, the student is super useful instead of trying to handle it. So some experiences from all of this stuff. As I mentioned before, writing this in OCaml, having two really strong tools to help do different aspects of the transformation was very useful. So Merlin, as I said before, is kind of like a library on top of OCaml's type system that deals with a lot of things like incomplete programs in OCaml, but also offers a kind of LSP-friendly API on top of that, which makes it much more simple to query what the types of things are. Trying to access the type checker compiler libs directly is best done by a professional, I would say. And the second thing is OCaml has a really strong ecosystem of AST-based transformations. So if you're familiar with OCaml, that's PPXs, it's preprocessors. And again, most of what we're doing here is transforming parse trees or ASTs from OCaml to Hazel, which is made much easier by having actually a library of tools for doing that. And then the last two parts that kind of work together in that there's plenty of OCaml programs both in industry and research, and the majority of them are not using incredibly complicated features, which OCaml does have kind of more features that would be harder to encode from OCaml to Hazel. But we didn't come across too many in our limited but still real world transformation of OCaml programs. And kind of related to that is that although they're seldom used, there is the module system, which is kind of extensively used for namespacing and keeping things separate. Since Hazel doesn't have that yet, it does make it hard to want to do this in a slightly more real world setting, which would involve a lot more work as well with kind of working with the OCaml build ecosystem to understand how all the different packages are coming together and how you might want to encode that in Hazel. Again, Hazel, this leads on to some kind of problems with Hazel in that it's only a web-based editor with evaluation, which means that kind of having the same compilation strategy as OCaml is not really available. And so I can't imagine a world yet where you would want to, say, transform lots of packages from OCaml's ecosystem over, although you could still do some of the more pure parts of OCaml. As I said earlier, type tools are fantastic for placeholders in a programming language, especially when you are transforming bits of one into the other and you don't have anything for some parts. The fact that Hazel is written in OCaml is brilliant in our use case because we can reuse their AST directly and do what OCaml's really good at, which is writing kind of compilers and transformations like this. And as I've said throughout, there's lots of features that are not yet upstreamed into Hazel, and until they are, it does make this a little harder, but it did unlock the ability for us to actually do some of this analysis that's being presented at Hatcher. So I think in many ways that's been really successful. But I think there are some kind of questions that I'm interested in. I would love to hear your own thoughts on this, which is obviously this is an incredibly specific transformation from one programming language into another, and in many ways carefully selected to probably have the most likely chance of being successful. But how do some of these differences between these two languages interact? And I think that would be interesting research, especially at a user level, which is Hazel is completely kind of described as a live programming language, so it's constantly being evaluated as every keystroke that you type. And because it can't enter kind of incorrect editor state, this is great for teaching programming. But obviously it doesn't perhaps scale to real world code bases where you have web servers and all these sorts of things, and you don't want to be running things every time you do a keystroke. So how does that change the kinds of errors that people are making? Again, as I said, we've kind of taken errors that people wrote when they wrote OCaml and brought them into Hazel, kind of making the hand wavy argument that says it's likely to happen given they're that similar, but it would be better to also understand actually what are the differences here. Perhaps live programming is better suited to not make some kind of normal errors that you might make in OCaml. And additionally, perhaps the gradual typed system in Hazel leads you towards making different errors that you might make in the more static one in OCaml. Yes, and I think everything that I've said after that is just more a repetition of the parts that came before. So I think that's everything I have to say about this. Thank you for listening, and I'm happy to take any questions.
So I really like the sort of graphical like type errors that you have. And I guess out of curiosity, like how closely does Hazel match up with OCaml in the sense that could you use Hazel as sort of like a front end producing better type errors for OCaml, possibly?
Yeah, that's a great question. I think so, to put some of them on screen, something like this, for example. The type systems are quite different between the two languages. I think in terms of these smaller, especially for pedagogical purposes, where you're kind of implementing things like recursive map functions for lists and this sort of thing, I definitely think it's a useful way to teach some of those things, especially because the translation at that point is almost purely syntactic between the two. And definitely for teaching, you know, why does the map function in OCaml have all these alphas and betas, you can jump over to Hazel and show actually you can write those out yourself, which you can do in OCaml, but I think in Hazel, because you have to get those types, maybe it makes a bit more sense. I think for anything after that, in more real world settings, Hazel's probably a little bit young to be able to cope with, you know, there's no, as I said, there's no module system and stuff like that, so it might be harder in that sense. For exactly whether it would work or not, you would probably need to ask someone with more type system knowledge of Hazel, and there's plenty of people at this conference doing that.
Yeah. So there are some questions from an online audience member. The first one is the corpus of your type of OCaml programs available from somewhere? How was it collected?
Yes, it is. It's on GitHub, and it's, I think if you look at the search for the dynamic witnesses for static type errors paper by Seidel et al. In fact, actually, yeah, that link will be, yeah, the data set, and it's available on Zenodo and also on GitHub. And it's made available both as kind of the keystroke, by keystroke kind of tracing, but also the end evaluated programs that are nicely kind of separated into different types of errors. And I believe it was collected as part of an undergraduate course where students were on some kind of editor online, and it was tracing them whilst they were asked to complete programming tasks in OCaml.
Another question, would the long-term plan be to add more features to Hazel, or add pause and then input it to a simple subset of OCaml?
I think probably add features to Hazel. I think the work done there to integrate type tools into all aspects of that language, the editor, the type system, the evaluation, is probably harder to try and put in. Like at the moment, Hazel is already kind of a subset of OCaml type tools. I think there could be work there for people who are interested in seeing the differences that would entail for type systems and how to build those. But I think there's a really strong set of students working on Hazel. And if you go to the Hazel repository, any of the branches are also deployed onto the website. And so you can have a play around with the new features as and when they arrive. So there's already a module branch, there's a the decomposable type highlighting is already on a branch there as well, so it's all good, available to play around with.
Thanks. Let's thank the speaker. This is it for the session. So we can go for a break.
Yeah.
That's true. So this means you'll be able to get in like musical modes. And the framework, always in the cosmos. You'll be able to put it on that or does it not include it already has something like that. Just need it. Yeah, it's a right, of course, it's just the generalization. Yeah. Other things are probably if you want this now. I mean, basically you are going to want it. There's probably some stuff you can do with mathematicity. Yeah, do. For search stuff. But then you have, say you do this kind of non-deterministic order. Yeah, that means that you can have like several paths for and you're redoing work. But you're redoing significant amounts of work. And you can think about applying reordering after one. So you have you have this. So each of these compositions will do a possible reorder. Is it possible to reorder after one composition? Perform some otherwise mode. Then the next piece of compositions, then like reorder it and stuff. Yeah, I think that creating paths that are simple, where you're now checking multiple different things. I'm wondering if you're doing like the only kind of proving that you're doing is impossible. That's basically that's a form of proof. That's how it is to do. Not doing any other form of proof. The base thing is kind of standing up all the time, checking everything. Yeah, quite similar to rewriting. And lots of those basically whenever they do this. Yeah, I like now. Right, exactly. So it's pretty dark. I mean, I'm not enforcing the universe, but if you even told about this in one of my lectures. I think it was the same idea, but oh yeah, sorry. Yeah. Thank you so much for organizing it. Yeah.
I think you need to borrow. Wow, like that must borrow from the.
You don't have it, or have self today going to open.
Wait.
Ah.
Oh
Yeah,
shit.
which is the speaker?
I think Gabriel is.
Co-host.
Yeah, I think he's a speaker, but the.
Actually, he can video then after flip the screen.
Video flip screen.
Yeah, means that because he got two camera, one front, one back, right? You got no laptop or what? How many camera laptop have?
Just online present.
That's
the problem. Online present okay, ma.
Oh.
We don't have the.
Yeah.
I don't know who's want to take also.
Yeah.
I didn't bring mine also. Oh wait. Unless somebody can. Is it difficult?
Huh?
Is it difficult to log into the Zoom and plug in the thing?
How to plug in? You need to let me know how.
I mean, just try. I can try to get somebody's.
How to log into Zoom? As in,
Oh
how
no.
to do the setting?
Is it possible to use like somebody's laptop and plug in? I can probably ask the maybe Louis or somebody and borrow theirs.
And I can try that. You try both first.
Okay.
Yeah. You look for it.
Okay. I text him first.
Yeah, you text him. I think I'm here lah.
Okay.
No point ask you right here. Okay. You also don't know where it is.
Because I also don't have.
This one can? This one can work?
Oh, actually maybe can. No, but to do USB-C. Oh yeah. Okay.
I have what?
Was just looking for you guys.
I have a USB-C.
So the problem is that so that camera cannot be turned at all, and that means that somebody needs to plug their laptop in, but the speaker is presenting. Gabriel is presenting remotely. So we were thinking either we use this or somebody's laptop to do it and then flip the screen.
I can go get my laptop with you.
Round for the camera.
Then because the camera cannot.
Yeah.
No.
So, okay.
So the other and so what?
This doesn't have a camera.
No.
It does.
It's just a HDMI projector cable mic.
Yeah.
Nope.
Sorry. Oh, sorry. You want to see the? Oh. Sorry, are you presenting?
No, I'm chair.
Oh.
It's my
Yeah. Sorry. I was confused. Okay.
But the thing is, the speaker wants to see the audience because speaker is presenting.
Yeah.
But that's the situation.
So so this camera cannot turn. So either you use my thing or we use somebody's laptop.
We can use.
Yeah, we can try, but no guarantee about compatibility and all that.
Yeah.
I can use mine. I have tested my laptop on these rooms many times. I think it should work.
Camera? Wait, sorry, I'm trying to.
Then can you check SR10? Because everything is on. The
close that, save battery.
The recording and the
Zoom live.
yes,
It's charging.
but it's not. We cannot find the live on YouTube.
Oh wow, it worked.
I think they are changing the room though.
But the camera though.
SR10, they want to move to a bigger room.
I think I need to.
So now
join the Zoom.
finish at the VC room.
How do I join the Zoom?
Yeah, so they want to move to VC.
Oh, but it's not fun. Which one is in SR10?
No, they want to move over. They want to change room now. They need a bigger room.
Because of the chairs.
Yeah. So now the
might be
SR10,
underneath here.
VC already finished.
Yeah.
Farm itself is really done.
Okay, so they.
So they have to move over.
Okay.
That's right.
Join the meeting.
You can do this meeting ID.
Okay, right. Thank you.
Which session is in SR10?
This one. Thank you so much, guys. I need to turn on the camera, but mute the mic.
Yeah.
Yes, correct.
that's right.
Recording in progress.
Oh, wait, the audio, can I?
You can mute your.
Tutorial 8B. Ascertain.
No, I want to disable the audio completely. There's a way to disconnect audio. There we go. Okay, there we go. Problem solved.
It's like the
There we go.
Oh, yeah.
Yeah, you can. Okay, problem solved.
But I don't think. I mean, I don't think you need to connect, right? Because as long as you join the Zoom as a participant, and then the speaker can still see the audience through your video,
Yeah.
which is going to be visible because you are one of the participants and you'll have the video on.
Yeah.
So this connection is unnecessary.
The triple contact.
Oh, what is the room of harm? Oh, good
VC.
point.
VC. VC vote.
But actually, can someone,
VCRN, video conference.
can I just have a charger to plug it in?
Yeah, in case no battery. Where's your power? I mean, I have a power plug in, power point here. But where's your charger?
I got. Luis, I need my charger back. But didn't you got it? No, it's charging your thing. No, but someone got the charger.
Okay, you can use mine.
Because when I arrived there, it was oh, maybe I don't know. So that's this information is correct, right? Tutorial 8B is moved from.
Yeah, correct.
10 to
I
0.
told my Philip or agent to help set up the Zoom
Okay.
for farm over the tutorial 8. Like as well? YouTube, like.
Specifically because I went to types.
I don't know because.
Recording it. Like for YouTube?
Yeah, it was recording and it was
Okay,
being
good.
streamed, but I didn't see the recording, so that's why I was asking.
Then I'm done. Let's go. I can go.
Designing. Stanford.
Just setting up the. Yeah, because one of the speakers later wants to see the room. Oh. Okay, we should.
Chair? Great. I have a request for you. Are you using this computer for the session? You are not using this computer for the session. What are you using for the session?
Only the remote, all presenters are remote, and the first one, will be.
So you'll be using the Zoom. My request is, I'm just gonna quickly pull this up. Tell your attendees to go to the concert and show this webpage to your attendees so they know how to get to the concert. This also tells them how to get to dinner. Just at the very end of your session, once everything is done, just change over to the browser and just tell them there is a concert, please go, and this is how you get there.
It would be better to tell that to co-chair of the session. I should I should tell him.
Okay, that works. Happy, whoever you'd like to tell, I just want to make sure the message gets across.
はい、終わったら、開いておいたから、これを見せて、バンドコンサートがあるから通知してくれなんて、終わるんだけど、これ私が言うことか。まあ、でも、僕が言っても、どっちが言うか。私はそういう英語はさらっと出てこない、英語小食人間なあれなんですよ。いや、なんか適当にやっていいな、適当にやっちゃいますけど。あと次話す人が、次の人だけライブストリームなんで、ちょっと今いらっしゃるんで、ちょっと通信が問題ないかちょっと聞いてみる。Hello, Gabriel, do you hear us?
Yes, I can hear you right.
Yeah, I can hear you very well. So, yeah, just so it's 10 minutes before you start talking. So just wonder if you want to test your audio or slide setup.
Of course, yes. So So then I should share my screen, check that it works. Wait. I need to decide. Tac. Okay. Let's try this. Can you see my screen being shared?
Yes, yes.
Okay.
Okay,
this
it
is,
should be working well.
yeah, so I will stop sharing and yes.
Yeah. Thank you very much for confirmation.
Okay. Thank you. I'll wait until it is done. Thanks.
Thank you. The second topic is actually being recorded. Yeah, also how the talk will also recording. So yeah, so I saw two recorded files with different titles. Okay. But I saw there was prevent from online exam.
Oh yeah, the last one was a
yeah. I assume that presenter will be there to respond to questions throughout the session. Yeah. At least I saw that. So that presenter for the second talk has appeared.
Yeah, he was here.
He's not. So Gabriel is the first presenter, and the second presenter was there.
Yeah. Maybe he will come back.
Yeah, I believe so. Okay, but time to start the session. So, it's time to start the third session of the presentation. And the first presentation is about code generation, program generation with satisfying the constraint. Okay. I will make it. Okay. Let's start the presentation.
Okay, so hello everyone, and thanks for having us present remotely. Let's present as a slideshow. Does that work? Yes, I think. Okay. No. Yes. Well. Of course. Anyway, so let's present like this. I'm Gabriel Scherer, and this is work that has been done thanks to the help of Hugo Barrero, who was an intern with me this spring and summer. I will be watching the Discord for remote questions. So if you have questions, feel free to ask them remotely. And the organizers kindly set up a small laptop in the front so that I can see the room, so I can actually see you. And if there is a problem, you can wave. And well, most of the time I've been looking at my slides instead. But still, you can do that. Okay, so the problem that we are working on is random generation for the purpose of random testing. And if you want to test, so random testing is pretty effective. And if you want to test a meta program, you need to generate valid programs. I work on the OCaml compiler, so ideally I would have a random generator of OCaml programs. And then generating a program that has valid syntax is pretty easy, but generating a program that is well-typed is in fact difficult. And the more complex your type system is, the more complex the generator would be that manages to generate a well-typed program. The problem is that as the type system grows more complex, you have to add more logic to your generator and also find some tricks to make it efficient enough and so on. and it grows into a monstrous pile of complexity. And the problem is that you already have one monstrous pile of complexity in your implementation, which is your type checker. So you don't want to have a second one. And the goal of this general research arc, if you want, is to find a way to use your type checker as a program generator, so that you have only one monstrous pile of complexity in your whole implementation and not two, that scales with the type system. So why is it hard? Well, of course, you can take a typing rule and read it from conclusion to premises as a generation rule. So for example, this typing rule for the application here tells you that if you want to generate, if you have a context gamma and you want to generate a program of type B, well, you can generate a random program T of type A to B, and then a random program U of type A, and there you go, you have made a choice of how to generate a program at type B. I call this leafward generation because you start with a problem at the root and you decompose it into sub-problems which are sub-nodes toward the leaves. Okay. The problem is, okay, if you know B, you will generate randomly T and U. How do you decide what A should be? Okay. And this is not so easy in practice. So you would think, okay, let's generate a random B, random A. So let's start by picking a random A. This is a terrible choice. So first, the search space becomes huge. And second, most choices of A will prevent you from either finding a T or a U that works. And so the generator will never, will become very slow and rarely succeed at generating multi-programs. So you have to use tricks, okay? And it gets worse because in addition to this pretty simple rule, you have polymorphism maybe in your system. Camel certainly does. And generating well-typed programs that do make meaningful use of polymorphism is more or less an open research question. So the most of the work on this problem has been done. I mean, there is a lot of interesting work by Palka. And the short answer is that it's hard and people don't really know how to do it. So how do you want to do this in a reasonably efficient way in terms of avoiding dead ends in the search space and backtracking? Well, what you want to do in the first rule, for example, is to, instead of picking a, you want to say, okay, there is an unknown type variable alpha that I will use instead of A, and then I will start generating T or maybe U, and that will tell me what alpha should be. So there will be some information propagated to learn what solution you want for alpha, and eventually you will get a complete type A, and in this way you will manage to apply this typing rule without blowing up the search space. So this is a natural idea. So one way to do it is to implement yourself in Prolog, which is very good at backtracking and unification. Paul Taro has been doing that in the 2010s, and he pushed this to the limit. So he has several publications on efficient, uniform generators of simply typed programs in Prolog. And then there is very nice previous work by the PLT Redex community, where they have a language to describe type systems in general. And for any type system described in their language, they come up with a custom constraint generator and solver that will do this sort of efficient on-the-fly solving of random generation constraints. The problem is that none of these two approaches scale to a type system of the complexity of OCaml. Okay, so Redex works well for monomorphic programs, but for polymorphic programs, it doesn't work better than previous works. And I don't know if I could convince the maintainers of the current type checker to switch to Prolog. I suspect it would be pretty difficult. So instead, I have to find another way to use something with unknown type variables and unification. Okay, so what's another system that works like this? So let me check my camera. No camera anymore. Ah, yes, it is here. So does anyone have a guess at a system that is used in an implementation of a programming language that use unknown type variables and unification? No. I can see people nodding, but no one is raising their hand to answer. So yes, one system that works like this is inline linear type inference. So the idea is, okay, we already have a system that does unknown type variables and unification. Maybe we can use it for a random generation. So the approach is that instead of trying to generate full typing generations, we will generate in untyped terms incrementally. And then we will run type inference as a way to check that these untyped terms, partial untyped terms are correct. And if we run them early enough, so during generation, we can avoid getting into dead ends with programs that are ill-typed. And so we did that, and it worked. So we have a prototype which can do random generation of well-typed micro ML program, by which I mean simply type the calculus plus let with Hindley-Miller style local generalization, so polymorphism. And this is built using a type inference engine, which we re-implemented for this purpose, but it's realistic. So it has the same design as Inferno, and we believe that it can scale to a type system of the complexity of OCaml. It has not been done, but it's plausible that it could work. So incremental term generation, well, the idea is you start from, okay, I know nothing at all about my term, this is the question mark, and then you pick a term former at random, so we are at the untyped level at this point. Okay, so let's do a let, okay, so then you turn this whole into a term that is partially complete with two sub-holes, two parts that are still to be filled. So you pick the first hole and say, okay, let's do randomly a lambda, for example, and there you go, you progress. And of course, there are several other branches that you could choose. So you can enumerate random untyped terms in this way, more and more complete. And the idea is that after each such step of generation, we will run the type inference engine, and we use a constraint-based type inference engine, so it generates constraints and then it solves them. And the trick is that you can solve, when you move from let to let with a lambda, you can solve the new bit of the new part of the constraint that comes from the lambda in the solver state that you had when you finished type checking the first partial term. So when you had only let, you end up in a certain solver state, and then you can rerun that state to work a bit more to type check the lambda. And if you do this, you get a sort of incremental type checking that will do just a small amount of work at each generation step, yet be able to kill the branches of the search space that would be ill-typed. Okay, so this is the idea, and it's pretty nice. A remark: well-typed terms are exponentially rare. If you have a large term, it's very, very unlikely to be well-typed. And so the naive approach that you could think of let's just generate a lot of untyped terms, and then we will filter out the ones that are not well-typed. Okay, so you start from any term, and then you filter out the ill-typed ones. That will not work because it's very, very hard to find a well-typed term if you start from just a lot of terms. You have to guide search incrementally if you want to have chances of reasonable performance. So these question marks look like holes. And so when people say holes in programming language work, including, for example, the talk of Patrick that we had earlier, actually they mean meta variables. There are two problems. So one idea for how to do what I just described is, okay, let's enrich your type inference engine with meta variables, and then obviously you can do this. There are two reasons why I didn't want to do this. The first is that handling meta variables is work, so there are maps of meta variables to their definition because you need to be able to instantiate them and so on. And also, it's not so clear how to do local let generalization in presence of meta variables. Because if you know about Hindley-Miller type inference, it relies on the fact that you first type check the definition of the let completely, you get a type, and then you turn the local type variables into for all quantified variables in the type scheme. And then in the body, after the in, whenever you see X, you can instantiate it with the known type scheme. But of course, if there is a hole in the let, in the definition, you don't know what type scheme to compute, and you are stuck after the in if you see an occurrence of X. So it's a non-trivial problem to keep doing Hindley-Miller style let generalization in presence of unknown parts of the constraint. It's an interesting problem, but it's difficult, and I wanted to avoid dealing with that at this point. So instead, we did something a bit different, which is interesting, and I wonder if some people have done it before, which is syntax with subcomputations. So the idea is that you take your abstract syntax tree of your untyped terms. So for example, here I have var, app, apps, let, and log for source level locations to get decent error messages. And then you parameterize all of it over a functor f, okay? And you add an extra node, an extra constructor in your syntax, do, which takes as subterm a computation in f.t that returns terms. So I apologize for the OCaml syntax at the type level. The type constructor is on the right, and the type argument is on the left, which is arguably the correct way to write application in mathematics, but no one uses it, so it's a bit confusing. But this is the type constructor. You can think of it in general as the monad, if you want, and this is a type parameter term. So at this type, a subterm is either some concrete syntax or a computation in f.t that returns a term. So for example, if you instantiate this with a search monad m, then the values of untyped term m.term are syntactic terms, and some of their subterms are actually search problems, and there may be nested search problems. Okay, so you can think of them as describing a set of solutions in a pretty compact way. And in particular, you can implement, this is kind of cool, I think, the generic untyped term. So this is something of type term, okay, that describes the superposition of all possible untyped terms, modulo alpha equivalent. So what does the generic untyped term look like? Well, we have a gen that takes an environment, a list of bound variables. So it's just the gen in the empty environment. So this is the closed generic untyped term. And gen that takes an environment is just a do node. And then inside you have a monadic computation, okay, that is a sum. So this is a search monad, so you can say, well, this is an alternative, a list of alternative choices, which is either, well, one of the variables from the environment of bound variables, or an application with two subterms that are themselves generic untyped terms in the current environment, or an abstraction, and then the subterm has an extra x free variable that it can use, or a let, and then the definition of the let is in the current scope, and the right-hand side is in the scope extended with x. And this term, it contains a computation that actually describes the set of all possible closed terms. So this is something you can do with syntax with subcomputation. But then the problem is, okay, how do you extend the rest of your type checker to deal with this weird do node? And the answer is, well, it's easy. You just add more do nodes. So for example, here is the inference function in the minor type inference. So it takes, well, in the Inferno style, it takes an environment, it takes an untyped term, it takes an inference variable that is the result type of the term, and then it returns a constraint. So this is the constraint generation function. It generates a constraint that once solved, if it is satisfiable, it will return a type term. So this is the Inferno style. So the constraint does not tell you only fail or success. If it succeeds, it gives you a fully annotated version of your input term. And so, for example, so to extend it with subcomputation, now you take an untyped f term for a random, some functor parameter f, and you return a constraint f type. So the type of constraints is also extended with subcomputation. So in your infer function, so this is, for example, the variable case is as you would expect in linear type inference. So you look up in your environment for a polymorphic scheme for x. You generate an instance constraint. So you say that the variable w must be an instance of this polymorphic scheme. And then in this Inferno style where you elaborate at the same time, the instance constraint, if it succeeds, it returns a list of type parameters that have been used to instantiate the schema. And then you can describe how to return explicitly typed version of your input term, which is the same variable x, where you did a system F type application of all these types. Okay, so this is standard type inference code. And then if you have a do node, so this is a do node for the term, the type untyped term. It contains an untyped f term f.t. So you can use the map operation of the f functor to apply type inference under the f.t. So you get back, if you look at the time of infer, you get back a constraint f.t computation, so f.t. So you get something of type f.t applied to constraint f.t type term. So, and this you can pack under a do node. So this do node is a constructor of the constraint type, and what you get back is a constraint. So you have a computation that returns a constraint, and you pack it under a do, and you get a constraint because our type of constraint has subcomputations. So pretty easy, just 2 lines that you need to add, 3 lines to your existing function to support subcomputation. Then you have a constraint solver, okay? So you have a type of normal constraint that is either a return or an error. You add an extra constructor and do for subcomputations. And then the constraint solver, you add a case that says, if I get a do in the constraint that I need to solve, I return a do in the normal constraint that maps over the resolution of the constraints below this P. And here you can, if you think about this, what happens with that is that the solver will stop on the first do node, and it will so here it will return a do event. It will so in particular if there is a do node within a let, it will never try to generalize over this. It will stop on the do node and it will wait until you decide to do something with this undo result to go further. So in a sense, the system will only see fully typed terms in the end, and you don't have this problem of legendization with rules. Finally, when you have a normal constraint that can contain some these do nodes, you need to get rid of the do nodes eventually. So if you know that M is a monad, you can implement a very simple function that takes a normal constraint and return a result, so either a value or an error, in the M.T monad. So when you see a do, you do a bind. And so recursively, so you bind under P, and then you run on every result, if you want, of P, you run the run function. This is a bit abstract, so just let's look at all of this together. In the case where M is a search monad, so you have this sum operator to add alternatives, you can define a generic untyped term, so you get an untyped term. Then we apply a cut size function to say, okay, I don't want all possible untyped terms, but only those whose size is 10, let's say, because otherwise my generator will blow up. Then I run the constraint generation function and I get a constraint with subcomputations in M that can return eventually a well-typed value. Then I can run my constraint solver and I get a normal constraint with subcomputation that can eventually return a well-typed value. Then I call the run function that we had just before, and I get something in the M.T monad that is the result. And then I can call the run function of the monad, so it goes from M.T to a type of infinite lazy sequences of OCaml, sec.t, and I can also filter out the error output, and I get a sequence of all well-typed terms of this size. So easy. And the point is that I had to add a bit of logic at every layer to work with these subcomputations, but it's actually easy to do. A short demo. Wait, this is time for me to check how I'm doing on time. Okay, fine. I need to change the way I'm sharing my screen for the demo to have a chance of working. Sorry about that. Yes. Yes, good. So this looks like a nice environment to run the demo. Okay, so let's ask for a random term of size 10, and I want to see the types. So there you go, and you can see that there has been some polymorphism going on because there are a lot of for alls in the output. The size 10 is not the, so here what you see is the elaborated term with the type annotations, but the size is computed only on the untyped term. So there is a lot of type information, but it doesn't actually matter for the size. And here you can see that our prototype also supports tuple. So this is a let that destructs a tuple, and here you have a pair of this and that. Okay, so you see different terms. I think, what did I promise to do in my demo? Yes, size 20, size 30, so let's do this. Okay, so this is a slightly larger term. This is a slightly larger term. Yes, and there is an exhaustive mode where I change the search monad that I use. Instead of having one where run does some random sampling of the search space, I can also list all the solutions in order, in the order determined by my generic untyped term. So what is the first well-typed term of size 30? For your eyes only, it looks like this. So this is a bunch of applications of the identity function nested together. Well, this is what our generator gives. If you use another generator, you will get another first term. And I can actually, I can ask, so maybe it's easier to see with 10, and I can ask for 5 of them. And you can see that, well, there is some regularity, and eventually it starts doing something different. Okay. As this was me going off script. Size 100. So some challenge. Let's ask for the time. Okay. So here is a large term for to crash your type checker, generated in 10th of a second. But let's do better and let's do 300. Or maybe I'll just do one. Okay. So you can see that at size 300, it starts taking a bit of time. Okay. 7 seconds. Not too bad. And then the output is really large because of all these type annotations, but it's something. Okay. As you can see, performance is an issue because if I ask for a term of size 300, it is a bit slow. It takes 7 seconds. This is not so good for random testing because if you want to test your program, you need to generate a lot of terms quickly. And you can say, okay, do I really need to ask for a term of type of size 300? Maybe not. But the quick check wizard tells us that it's good to run. So even though most bugs can be reproduced with small inputs, let's say size 20, it's good to run the test on a large input, size 200, because an input of size 200 is more likely to contain the weird part of size 20 that makes the program crash. So in a sense, you get better coverage by starting with very large terms. So it's not realistic to do random testing with a generator that takes, let's say, 10 seconds to generate a new sample. So you need to have a generator that is well below 1 second and generates large enough terms. And so the current performance of our tool, I think, is adequate. It's not great, but it's not bad. I have not actually tried plugging it into a random testing framework, so I cannot tell you about bugs it would find and so on. But I can say that we did have to optimize the implementation of the search monad. I started with something very naive, and it did very badly. It would only scale up to size 15 or something. And now we have something that scales up to size 200 or more, despite supporting in-laminar polymorphism, which I think might be a first for a random generator of well-typed programs. At least most examples deal with simply typed number calculus with heuristics on top to deal with limited amount of polymorphism. Of course, we don't handle general system F style polymorphism. We are in a restrictive framework, but we can generate any micro ML well-typed. So if performance is an issue, it means you get to see pretty pictures. So the pictures were all done by Hugo, my intern. So this picture shows you the average generation time for a given size. You can see that for small size, it's instantaneous. For size 100, it takes a third of a second. For size 150, it takes about 1 second. And then if you move larger, so we were kind of lucky with, so this is on Hugo's machine. Maybe my machine is better and my average is lower, but we had a 7-second run at size 300, and on his machine, the average is more like 16. And then if you try to go higher, I mean, you wait too long. And this is average, but in our experience, the runtime is sort of, it feels like you are sampling an exponential curve. So sometimes it's much, much longer. And sometimes it's much faster because if it's an average and it's only 60, and sometimes it's much, most of the time it's actually faster than that. Okay. So this is an approach to compare. So we compared with the naive approach of rejection sampling, that is generate untyped terms, and then you filter out the one that are ill-typed. And the way we do this comparison is we define a timeout to be at 10 seconds. So you try to generate a term. If it takes more than 10 seconds, you fail. And then you try to do that many times, 1,000 times, and you look at the ratio of attempts that succeeded. Okay, so here you can see on the graph on the left that with the naive rejection sampling approach, which you can implement with a off-the-shelf type checker without doing anything special with holes or incrementality or anything, all attempts at generating a term of type 10 succeeding below 10 seconds. The failure percentage is 0%. But then if you move at size 15, 30% of the time we did not succeed in generating a well-typed term in less than 10 seconds. And you can see that the generator quickly becomes unusable with our implementation of type checking. So for the size 50, there is no chance of seeing a run. Well, there is very little chance of seeing a run that takes less than 10 seconds. Whereas for our generator, we are at a 0% failure rate, so we always take less than 10 seconds at size 200, and we still can generate about, so we fail 1/3 of the time with size 300, and we can actually push the generator until size maybe 500, and then it fails most often. It takes more than 10 seconds. So you can see that there seems to be a large gap in performance between the two. The intuition is, I believe that our approach is exponentially faster, but I don't know how to state that and check that formally, so I would be careful. At least it's much, much better, and it generates things that you could not hope to do with a naive approach. And finally, this is the last. Yeah. To stop for questions. Yes. Okay, so I'm done. Let's take questions if you have some. Thank you. If there are questions online on the Discord, I'm happy to take them, and otherwise I just listen. Yes.
Let's say again. Yes. Before let's think from talking about the prompt programming with type, bell type, or not type system, but some kind of type and constraint. So seems we have presenter, so yeah. Hi, RPG, do you hear us? So we have pre-recorded video, so we will play that, but so we want you to be present for Q&A session. Not responding. Message? No message? Hey, Abhijit, do you hear us? Chat? Yes. Okay. Okay. Then we will just start pre-recorded.
in count. Okay.
Thanks everyone. I'm Obhijit Pal. I'm from University of Dhaka, Bangladesh, French graduate. And my work is a drive-driven programming from task interfaces to a calculus of constraints. I'll begin by discussing what is prompt. Now, we all have used prompt. Literature have divided prompt into two parts, system prompt and user prompt. I'll focus on system prompt example here. The instruction is you're given two items, a sentence and a word content in that sentence. Return the first of the speech tag for the given word in the sentence. The input is the cat at the hat, and the target word is hat. The output is noun. So this is a structured system prompt. And for user prompt, it is our general question to the LLM. For example, what is dependent type system? Now, this distinction is necessary because system prompts are being widely used across commercial and research applications. For example, Duolingo, Apple Intelligence have services such as notification prioritization, agentic usage of mobile applications that likely uses it. So more concretely, we have numerous SPLASH and analytic literature that uses this structure. For example, from topic modeling, use TyDe. They essentially instruct the LLM to extract for a large data set and return a structured output. So this is a canonical example of system prompt. And this description of system prompt is necessary. However, most of the prompt programming literature does not mention this distinction in their research. And the reason is the difference is often blurry. We can look at code generation. For code generation, if we ask LLM to generate some code, these can be considered user prompt. However, if we have a system prompt explaining our requirement programming language that is always fixed, in that case, it can be considered a system prompt. So the distinction is somewhat blurry. And most important characteristic of system prompt is that it is fixed. Like software, it occasionally it remains fixed for a period of time. And that is the reason why we think prior literature should mention system prompt, because they intuitively uses system prompt, not user prompt. Because when you are compiling a program that is prompt, or when you are optimizing a prompt, when you are constraining a prompt using type system, you need a fixed prompt. If the prompt changes frequently, and those approaches become useful. So literature innately and inherently uses the system prompt. That's not explicitly mentioned. This is a caveat I just wanted to mention before going ahead. Now I'll look at the example of prompt programming. So we can have an example app called TyDe, which is similar to Duolingo. Now in TyDe, users can write a sentence. TyDe will use LLM to get the percentage of the word that the user needs to. and then it will generate more examples for that parts of it. In this case, now, and show it the user. As you can see, LLM is acting as a software component here. Given an input, it generates some output. Now, this is a very credible use of prompts inside a program, the software component. And these images are taken from Duolingo. And the final example is text to SQL. These essentially motivated this. When I was working on text to SQL, I had instruction like that, and then I would give a schema of the database, and it can come from a retrieval system such as RAG or role-based system. And then we have the natural language question and the SQL output. The important thing is the SQL output must follow SQL syntax. So this is a syntactic constant. And I was looking for a solution to enforce this syntactic constant for essentially output validation. And there are many open source tools. Proof tools use a simple type interface. For example, here the type of name is a string, hobbies is a string, very basic type interface. And there is PIML that essentially structures the entire prompt. So instead of plain string, you have structured kind of string. And then you have, again, simple type interfaces that determines what goes. And most importantly, even polymorphism or other type system that is available, you can compose really complex type systems in PIML. And then look what motivated the developers to use these type interfaces for prompts. And they saw this example. Traditionally, we would use to return HTML as a string, but now we use something more structured. And this is because, and I quote, the idea of maintaining hundreds of API strings for prompts kind of systems. So maintainability is a concern that motivates structured prompts. And then we found more libraries. For example, LLM.txt uses a structured prompt much like a program. And Instructor also uses a structured prompt. And tech giants such as Microsoft have also started projects on it. For example, TyDe constructs prompts using type. And it also validates the response using schema or type system. And if the output does not conform to the type system, it prepares by prompting the LLM again with the error from type change. This is the example taken from the documentation. So as you can see, the output is well typed. Each of the values has type annotation associated with it, and they conform to this type structure. And recently, Stanford Energy has also entered this space with their big project DSP White. As you can see, they can compile prompts. So what does it mean to compile a prompt? You compile programs to be faster, to be more performant. Same goes for LLM. To compile LLM so that it gives the best result efficiently most of the time via searching. So this cp.compile function can compile prompt, just like a program. And they also use some structure here, so they don't use tag system because NLP focuses on the analytical mode. So we have this three writing philosophy. Maintaining hundreds of asset strings is annoying. So developers build libraries with structured prompts. Output required as a software component. So developers build type validation. And we need to compile the prompts to optimize the prompt. So developers build heuristics to optimize prompts. And we can map this literature into a traditional layered structure of the prompt program. So we have the input layer, the business logic layer, the output layer, and a program naturally interacts with many other components here as well. And we can map existing literature in each of the cells. And very surprising also, all of the boxes have prior basis on it. So independently, developers are successful exploring many things, but they are conforming to a structure of the prompt program. And this finding started our research. And another recurrent pattern is use of tag system. As we saw in the previous example, almost all of the users project they use tag system for LLM output validation, constraints. So this is also an observation that our business hasn't pointed out. Now, the notion of prompt program not coined by us, it is already laid out there. Speech plan first mentioned this idea, however, mentioned it abstractly, and in this extended aspect, we solidified this understanding from the history. And most importantly, we show the use of tag system as a recurring pattern that hasn't been studied before. And to find more support as tag system is a recurring pattern, we identified 13 constants for prompt. And notice that 9 of the constants have been added, often in the form of tag system. And there are 4 constants that haven't been covered, domain constants, tone constants, etc. And we notice that there's semantic in that. So literature has covered syntactic constants, not semantic constants. Now, this is a very credible research direction. How we can incorporate semantic constant, perhaps by a probabilistic study. After finding, we have prompt program that often uses tag, and we have prompt constant often in the form of tag. So there's tag-driven prompt programming. So it was all laid out. So we formally define tag-driven prompt program as a dependently tagged code calculus with probabilistic refinement that treats prompts as type program and constraint and type refinement. We want to emphasize probabilistic refinement because to handle the stochastic nature of LLM, and most importantly, the semantic constraints we mentioned earlier, we need probabilistic refinement. And essentially, prompt program is a code tuple. We have the input output, and the prompt is essentially the LLM section, and the epsilon here means the parameter of LLM. For example, 10 parameters. And here's the constraint, type of constraint we can have. The 13 constraints can be here. And here's the example of how we can explain real world example using this definition. So this is the text to SQL task. We have the input with the constant is natural language, output with the constant valid position and no valuable information, and LLM finally constant. So constant line here is a domain constant, which is a semantic constant, that the output should only be about this domain, which essentially is a guardrail rather than. And we also identify some focus on the research. So there have been 6 interfaces as we have found. And there are also parallels on decoding, which we'll discuss later on. And there have been also research in constraints along with the type interfaces. However, there have been few research on program optimization or program compilation, or reusing the whole program as a type system for end-to-end optimization. That hasn't been done yet. This is a credible research direction that this experiment that suggests. And then we have the input and output type. We'll discuss each of the layers now. So we have input and output type. So this is the input type definition, and here is a more type example. For example, coffee option quality can be light, regular, or an integer. So a simple type interface. Similarly, we have optimization of prompt. So prompt is optimized via summary, meditation, finding few short examples that are most suitable, because LLM is stochastic. Just changing a word can impact the performance. So summarization, finding better examples, reordering, restructuring, this meditation helps improving, optimizing the prompt. So progress settle, there's a lot of meditation, feature example picking, and text which mutation the base result, and they combine it to form the mutated prompt. Now, this surface space is very large here. So what we propose is that this is just to show how much research potential type-driven prompt programming holds. So we show an example that progress setters in the domain is large. We can add our domain specific constraint to limit the start distance in very significant way. So we take some X from a distribution, we apply it to generate mutated program E prime, and then we take that, we ensure that the mutated program conforms to our constraints. And we can also prune constant data. For example, if our constraint need is enough, we only take the mutation that satisfies the constraint. So this is us applying the mutation that satisfies the constraint. And we can formalize it using a simple theorem that if our modified program comes from a mutation that is valid, then it will satisfy context we have. And it has been rigorously studied. So for post-hoc constraint, it is done by validating the JSON schema against the type system. And if it is not validated, we send it for it again. And we also guarantee that if our output is Y, the Y must constantly from the semantic constraint. And most importantly, there is constraint decoding. So constraint decoding is interesting, that we'll discuss now. So how LLMs generate output text by text, token by token. So what constraint decoding does is it masks the tokens that we don't need now, and then do it by offering type reachability. So it is used in programming language. So given the current code that has been generated so far, incomplete code, we generated incomplete graph of the program, and then we generate the number of reachable paths using that system. And we pick the ones that are most credible not everything is dark is there. So this is an example of constraint decoupling. And these approaches are what people, but it also suffers from not considering the other layers and also anti-monitoring. So in conclusion, we provide a synthesis of this emerging idea from programming origin, right? But this notion of type system across literature, currently only 4th generation class uses explicitly type system or mentions it. However, we showed that open generic type system for from program. So there is this emerging trend between academia and open source industry using type system in from program. This is a core focus that the focus of LLM research has a tangential shift towards type system. And they found 13 constraints for the diversity of the prompt, and we identified 4 prompts that hasn't been studied before, a more systematic concept. And we also showed 3 examples how type system can improve from programming using a constraint programming optimization. And we think it is a very interesting research direction, this extended abstract proposal, because LLM are using, and I'll end my discussion with a recent case. So GPT-OSS was released as open source software, and GPT spent millions and billions to ensure it is safe. However, developers broke it using simple perturbing. So we can't ensure enforcement of constraint via training. We need something like tax system to come to the rescue. For LLM from safety, from structure, from semantic, from syntax, tax system has come to the rescue. Thank you. Do you have any questions? Just to reply.
We ask present develop here. Before that, Abhijit, so could you turn on your mic so that you can answer question?
Yes, I'm available in my.
Have you tested your LM generated code against have any like test cases demonstrates how often work? You hear me?
Okay. Oh, little bit hard to hear the room mic.
Maybe I'll just ask them.
So maybe you can come here. And that's what President voice should be.
Can you hear me now?
Yes, I can hear you.
Okay, yeah, good. So have you tested your approach on like realistic scenarios? For example, do you have a set of test cases that shows how often could your synthesizer program generate type corrected programs?
We have experimented on the text SQL test we are doing, and we plan to submit our results soon. But it is not included in the presentation currently.
So is there
So for the text SQL test, we use the type system to repair the generated syntactic constraint, but it takes a lot of retries to get the correct syntax most of the time. So currently we are trying to improve it. How can we get the correct repairs at the minimum number of retries?
Okay. Yeah, thank you.
Thank you.
Really great. Afternoon. So, hello, Abhijit, can you hear me?
Yes, I can hear you.
So, my experience with LLM is probably much less than yours. When I haven't actually asked the LLM to produce any code, but just like following up on the question that was just asked, if the code does not type check, and with my understanding that LLM, there's a kind of stochastic nature to it in the sense that when you ask the same question twice, you probably won't get the same answer, right? So in your experience, when you get something that does not type check or the code is obviously incorrect, is it worth it to ask it to try again?
Yeah, so if we give the error trace, most of the time it can generate a better result. So providing more context based on the error that we encountered typically improves result. It depends on how much context you can provide to the LLM. That really controls the output. So in practice, we saw that if we give more error trace, the output seems to be converge faster. So
the point is to give it more information, like the output of the error, the output of the compiler, like where the error is, and then it will iterate and maybe give you a more correct answer. Okay, thank you.
Okay,
thank you.
To present the finish the presentation. So let's send to the speaker. Okay, the next presentation is the last presentation of this year's TyDe. It's about opacity of the definition.
Hi, Eve, can you hear us?
Yes, I can hear you.
Yes.
Yeah, so we'll start recording, but so it will be live streamed. Is it okay?
Yes, that's fine.
Okay, thank you. Thank you for confirmation. Okay, let me check. So, yes, it's fine.
Today, I will be presenting a formalization of opaque definitions for a dependent type.
Let me just pause it. Okay, this should be okay. Okay, then let's start. Can I?
Today, I will be presenting a formalization of opaque definitions for a dependent type theory. This is work done at Chalmers University of Technology and the University of Gothenburg in Sweden. So to begin with, what is a definition? In ACTA, a definition consists more or less of three parts: a unique name, which is used to refer to the definition; a definiant, which is the term that gets bound to that name; as well as a type annotation for that given term. This works both at the term level, as with this doubling function here, as well as at the type level, which we might call a type alias. Here, we define a positive natural to be a natural number n, paired with a proof that n is greater than 0. A key property of these definitions is that they can be composed in the sense that a later definition can reference an earlier one. So here's a classic example. Starting from the usual unary natural numbers, we can build a number hierarchy with each layer defined in terms of the previous one. So we can define integers as differences of naturals, where x comma y represents the integer x minus y. Then define arithmetic inequality in terms of these operations on the natural number type. Then we can define the rationals as the field of fractions over the integers with the usual equality relation given in terms of the operations on the integers this time. So now let's say that we want to show that this equality relation on the rationals is symmetric. This would be a proof obligation. Given a proof that x equals y, how do we produce proof that y equals x? A reasonable first step might be to ask Agda to normalize the goal type for us, which gives us this. And that's not very readable, right? So what exactly is going on here then? Well, when Agda normalizes a definition like equals q, it unfolds it, replacing it with its definitions like this. But now we have an equals z that also needs to be unfolded, so we get this. And then finally, unfolding times z, we get that big block of text from earlier. Essentially, the problem is that we've gone from this high-level concept of equality on Q all the way down to the lowest level of operations on the naturals. And to be precise, the problem is twofold. First, while it's fairly cheap to unfold any individual definition in an expression, the process of repeatedly unfolding all of the definitions in many deeply nested expressions can quickly blow up, costing considerable time and memory in the type checking process. And on the other hand, I, as the programmer, am also not very fond of this block of text. As a goal type, it's not very readable, nor is it terribly enlightening as to exactly what it is that I'm trying to prove. So what recourse do we have? One possibility is to adopt opaque definitions, which are simply definitions that do not unfold. In Agda, this is accomplished using the opaque keyword like this. But of course, if the definition never unfolds, then we can't meaningfully reason about it. So we can use the unfolding keyword in the context of another opaque definition to declare that inside of this scope, we do want the definition to unfold. So the idea then is to define a sort of interface to the opaque definition that allows outside code to reason about it without having to explicitly unfold it. For example, equals z and times z here can be thought of as part of the interface to z. Then when we're consuming z elsewhere, we can just use this interface like so. And the key thing here is that we haven't actually given an unfolding clause for z anywhere, and so it will not unfold during type checking. And to see what this means for us, we can look at our symmetry theorem again. Since we want to reason about the internals of equals q, we make sim q opaque and then add the corresponding unfolding clause. And then if we ask Agda to normalize the goal type again, we get this time. So note how it's given in terms of the operations on z now rather than on n. And in fact, if we take a look at the unfolding chain from before, we can see that this goal type is what we got after only the first unfolding step for equals q. Since we didn't ask the type checker to unfold anything else, this is as far as it will go. So the upshot of all of this is that the opaque definitions seem practically useful. We can use them to locally control unfolding, which can help improve both type checker performance as well as the user experience. But the question then is of whether they're actually semantically sound or not. In particular, since it changes the way that definitions reduce, it's conceivable that opacity could have an impact on subject reduction, and this is the question that we're going to seek to answer here. So our contribution is as follows. We give a formalism for top-level opaque definitions, which is based on the way that opaque definitions are implemented in Agda. And moreover, we have a full formalization in Agda of a dependent type theory with support for these top-level opaque definitions using our formalism. It builds on the existing graded type theory project, a formalization of a graded model dependent type theory, which in particular lacks support for definitions of any kind prior to our work. And finally, using this formalization, we've established a number of desirable properties of the type theory, including the aforementioned subgrid reduction, as well as normalization, consistency, decidable type checking on a certain fragment, and so on. So let's start by talking about how we formalize definitions without opacity. Here's a quick overview of our core language. For the most part, it's a fairly standard dependent lambda calculus. The interesting part is the addition of definition names alpha, which are treated in much the same way as variables x. There's a minor difference in that variables are represented by de Bruijn indices, whereas definition names are represented by de Bruijn levels, reflecting the fact that definitions are invariant on their binders. But what is it that these levels are actually indexing? We define a definition context nabla to be a list of definitions in much the same way that the usual typing context gamma is a list of variables. And each entry in nabla is a pair of a definiens t and a type annotation a. We can see that this is in fact exactly the same information that's contained in an AGDA definition, shown here with t equals lambda n plus n, and a equals nat to nat. These definition contexts will carry information about all of the top-level definitions that are available in the environment. And since the typing rules for definition names will need to look into the definition context, we'll introduce the nabla now into each of our typing judgments, like so. And we'll also need a new well-formedness judgment for a definition context, which is defined as follows. A definition context is well-formed either when it is the empty context, or when it's a well-formed context nabla extended with a new definition t annotated with a, such that t is a well-typed term of a. And since we're considering top-level definitions, this happens in the empty typing context, since there are no variables to speak of. Additionally, we modify the well-formedness rules for typing contexts so that the empty case requires a definition context to be well-formed. This dependence of typing context on definition context makes sense when you consider that a variable may have a type given by a type alias, such as int equals nat times nat. As an example, consider the definition context with the two definitions double and quadruple as shown here. Show that it's well-formed, it suffices to show that in the empty definition context, the term lambda n plus n, which is the definitions of double, is a well-typed term of nat to nat. And then that in the definition context containing double now, the term lambda n double n, which is the definitions of quadruple, is also a well-typed term of nat to nat. So now let's take a look at our new typing rules. The defin rule here states that in a well-formed context, a definition named alpha is a well-typed term of a exactly when it refers to a definition annotated with a in nabla, which is what this notation here means. Essentially, this rule is stating that a definition gets its type from its type annotation. So for example, in a context with double, alpha naught refers to double, which is annotated with nat to nat. And so we can conclude by defin that alpha naught is a well-typed term of nat to nat. Next, the delta reduction rule states that in a well-formed context, if a definition named alpha refers to a definition with definiens t and type annotation a in nabla, then alpha is actually equal to t as a term of a. And this rule is, of course, what gives definitions their substance. So using the same example here, we know that alpha naught refers to double, which has the definiens lambda n plus n, and so we can conclude by delta reduction that alpha naught is actually equal to lambda n plus n. And finally, we have another variant of delta reduction, which applies to the actual reduction relation. So it's essentially just a directed version of the previous rule, which states that a definition name reduces in a single weak head reduction step to its definiens. And that's about it for top-level definitions, really. We have two rules governing the well-formedness of definition context, and then three rules giving meaning to definition names. So now, how do we get opacity into the mix? To begin with, we'll need to mark each definition as either opaque or transparent. And to do this, we augment the extension case for definition context to include an opacity omega, which is either opa, meaning opaque, or tra, meaning transparent. We'll also need to keep track of which other definitions an opaque definition wishes to unfold. And so the opaque case includes an unfolding vector phi, which is a bit vector demarcating the prior entries in the definition context, which have been named in unfolding clauses. This should be a bit easier to make sense of with an example. So let's suppose that we have a definition context with the three definitions z equals z and sim z as shown here. Since all three are opaque, all of the context extensions will be marked with opa, like so. And for z, there are no prior definitions to unfold, so the unfolding vector is simply empty. For equals z, there is an unfolding clause for z. So the unfolding vector will have a 1 in the first position, indicating that it wants to unfold z. And then for sim z, there's an unfolding clause for equals z, but not for z itself. So the unfolding vector will have a 0 in the first position, and then a 1 in the second position. To actually use the unfolding vectors in the typing rules, we'll define now the transparentization operator, which expresses how unfolding vectors act on definition contexts. The idea is that an opaque definition lives in a context that has been transparentized by its unfolding vector. And what this means is that prior definitions that it's asked to unfold will now appear transparent to it. Of course, the empty case is trivial. And in the no case, we consider a vector phi with a trailing 0, meaning we don't want to unfold the outermost definition. And in this case, we don't need to do anything, so we just copy the definition from the input to the output without touching its opacity omega. And then continue on with phi on the rest of the definitions. In the yes tra case, we consider phi with a trailing 1, meaning that we do want to unfold the outermost definition, but the definition is already transparent, so there's nothing to do. We just copy it over, leaving it transparent, and then continue. The interesting case then is the yes opa case, where phi has a leading 1 and the next definition is opaque. In this case, we copy it over, turning it transparent in the process, and importantly, we continue not just with phi, but with phi joined with the definition's unfolding vector phi prime. And this joining operator here is just bitwise disjunction. It enforces the property of transitive unfolding. What this means is that when a definition unfolds another definition, it also implicitly unfolds all of the definitions unfolded by that definition, and so on and so forth. And we'll see why this is important later, but first let's take a look at an example. So suppose that we want to apply the unfolding vector 1, 0, 1 to this definition context from earlier. First, since the vector is a trailing 1, we want to apply the yes-oba rule to make SIMZ transparent. Thus, we join the leading part of the running vector with SIMZ's unfolding vector to get 1, 1. And then, since there's still a trailing 1, we can apply yes-opa again to make equals z transparent. And again, we join the leading part of the running vector with equals z unfolding vector this time to get 1. And then finally, we apply yes-opa one more time to make z itself transparent. And so thus, we can say that 101 transparentizes this context to make everything transparent. And we can see transitive unfolding in action here in that we made equals z transparent, despite the original unfolding vector having a 0 in the second position. Since SimZ wants to unfold equals z, the join in the first step placed the 1 into that second position, and so we ended up unfolding it anyways. Now to account for opacity, we split the extend case of the well-formed misjudgment into a transparent and an opaque case. In the transparent case, it's exactly the same as before, but in the opaque case, we now need to transparentize the context in which the definitions is checked, so that the prior definitions it's asking to unfold will correctly appear transparent. Note that the type annotation is still checked in the original context. This is necessary to prevent the definition's type from leaking any implementation details of the things that it unfolds. So for example, consider this lemma. For the type annotation to make sense from an outside perspective, it would either have to be the case that these pairs here can be typed with a z, or that equals z can be typed as a binary relation on pairs of naturals. But neither of these things can possibly be true without unfolding z, so that type annotation actually is ill-formed. Now for the typing rules, if we redefine the maps to relation here to only hold when the definition in question is transparent, it turns out that the exact same typing rules just end up working. So the defin rule still works anywhere, but the delta reduction rule will only go through when the definition is transparent, giving us the desired mechanism for controlling unfolding. So now let's talk about some results. Our key technique for reasoning about normalization is a Kripke logical relation. Roughly speaking, the idea is to define increasingly stronger variants of the typing judgments that characterize terms by the weak head normal forms. Then, by proving the fundamental theorem of logical relations, it's possible to show that all of the variants are in fact logically equivalent, and this is actually one of our core results, that our extensions to the type theory preserve the fundamental theorem. So a few normalization-related consequences fall out of this. Of course, we have the usual normalization theorem, which states that any well-formed type or any well-typed term reduces to some weak head normal form. And we also have canonicity for the natural number type, which states that in fully transparent contexts, all natural number terms are equal to numerals. In particular, this requires transparency because it might be the case that an opaquely defined natural number does not reduce because of its opacity. And finally, we have consistency in the empty context, a form of canonicity for the empty type. Now you remember that bit about transitive unfolding from earlier? The main reason to enforce transitive unfolding is this theorem here, which states that well-formedness of definition context, as well as certain other typing judgments, are preserved under transparentization. And this is analogous in some sense to subject reduction for transparentization. And in fact, we also show that with explicit unfolding, that is the system where we only unfold exactly what we ask for and nothing more, there exists a transparentization from a well-formed definition context that gives back an ill-formed one. Some other miscellaneous results include the usual sense of subject reduction, which states that types are preserved under weak head reduction, as well as decidable conversion, which states that given two well-formed types, it's decidable whether or not those types are judgmentally equal. And moreover, given two well-typed terms of the same type, it's decidable whether or not those two terms are judgmentally equal. And finally, decidable type checking, which simply states that on a certain checkable fragment of the language, all of the basic typing judgments can be decided. In particular, the formalization contains a bidirectional type checker, which we have now extended to account for definition context. So in summary, we've given a formal characterization of top-level definitions, which may optionally be marked opaque to restrict unfolding. We've implemented the formalism as an extension to the graded type theory project, which in fact has now been merged into the main project with certain changes. And we've shown that our extensions preserve many of the desirable metatheoretic properties of the theory, including subject reduction, normalization, consistency, and so on. And finally, we have a full mechanization of the formalization in ACTA. If you want to check out the code, you can take a look at the Zenodo record linked below, or the version of the code bundled with the paper. Alternatively, you can check out the GitHub repository if you want to see the development version of the code. Thank you for your time, and have a fantastic evening.
Okay, let's turn to the speaker.
Let's just confirm speaker on screen. Okay. Also, could you turn on microphone so that you can answer questions?
Yes, yeah, you can hear me?
Yes, thank you.
Good.
Any question?
Please come here and ask him.
So that is microphone.
Yeah. Can you hear me?
Yes, I can.
So in the system as presented here, this concept of opacity only applies to top level definitions, right? Is that
Yeah.
Is there a fundamental like reason why it only works at the top level, or could you have like local definitions inside of something else also be opaque or something? I don't know why you'd want that, but just wondering if it's like possible.
Yeah, it is possible. In fact, there are some systems out there that implement it, like the rock type theory. But we elected to go with only top level definitions for this project. One, because it better models how ACTA works. It only supports opacity for top level definitions. And two, because the formalism is slightly simpler. One thing to note about having local definitions is it's possible to have interdependencies between variables and top level definitions, because you could say have a variable be a type variable, and then you would have a local definition that depends on the type variable, since the definition is typed with that type variable, right? Which means you would kind of have to intersperse the definitions and the variables in some kind of heterogeneous context somehow, which is a little bit complicated. But in principle, there's nothing actually stopping you from it if you want to go through all of that trouble, yes.
I see. Okay. Thanks.
Yeah, so on that point about it modeling actor closely, what about parameterized modules? Because then you are extending the context, right? You can introduce additional variables, and in that circumstance, you know they're not going to depend on the definitions at the same time, right?
Right. We're sort of in some sense thinking about an idealized version of ACTA where it's mostly just the basic calculus and not any of the fancy types or module system stuff.
I'm wondering if parameterized modules would be easier to figure out than local definitions.
Probably.
Yeah. Okay.
I'm not sure. I haven't really thought about it.
Okay. Thank you.
Sorry about that.
Okay, I read the question. When all definitions are transparent, if I understand correctly, two terms are either equal or observationally distinct. With OPEC, now there are cases where we cannot prove equality, but in fact the terms are not distinguishable. This could create issues in implementations that bake in the assumption that non-equal or incompatible implies distinct. Do you know if this has bitten people in practice?
I don't think I caught that. Is it possible to maybe type the question in the chat box?
Okay. You have access to, I'm sorry, this copy.
Oh no, I'm not in it. Sorry.
Maybe just copy it into the Zoom. Yeah, let's copy the question. Oh, okay.
Okay, thank you. When all definitions are transparent, if I understand correctly, two terms are either equal or observationally distinct. With opaque, now there are cases where we cannot prove equality, but in fact the terms are not distinguishable. This could create issues in implementations that baked in the assumption that non-equal implies distinct. Do you know if this has bitten people in practice? I do not know. I don't think I've actually seen that in practice. I don't think I can provide any more information about that. I'm sorry.
Okay, maybe the first, no, okay. So, it's 5 minutes or so left.
Other questions? So this is our last chance for questions. So maybe I can ask a very general question. So as I understand, you have added the opaque to a specific type system. But if we want to add similar like opaque definitions into other type theories, like how could your approach be generally applicable to them? Or do you foresee any difficulties in adopting your approach and other type systems?
No, we think that it should be fairly generalizable. And in fact, you could even, I think, remove the dependent part of the type theory to create a sort of non-dependent definition system in any sort of type theory you want.
Okay. Yeah, cool. Thank you. There's no other questions. Let's thank the speakers again. And this concludes this.
Thank you. Have a good evening, everyone.
Thanks.
The workshop finished here, but we have also the concert by the PRAM workshop, it's workshop or I'm not sure. And check the web page of the web venue.
So, hi everyone. So there will be farm concert in Utah. Yeah. So this shows, I have this shows guide, but I'm not sure where it is. Okay. At least you can check out the guide from ICFP homepage.
Yeah, so, actually, I'm not familiar with this. Yeah, yeah, someone, I don't know, I saw, there's supposed to be a student when. Are you a student when? You're from the AS. You're not from this. Yeah, I'm from Japan. So I don't know about campus. Yeah, but yeah. So if you go there, then there is some student volunteer who knows better than me about where to go. So yeah, if you wanna go from concert, then just get out and follow. Yes, that's not. Yeah. Much greater than that, or because no, even the last one, yeah. And this is definition, so many more formats. Even more, well, I'd say more ship. Just term. Like the cost is too high. But yeah, this is not your country. It's very. In ACTA, most cases you're working with or under construction. Yeah. Yeah. Well, they did something for, well, quite a few people. Yeah, Gabriel told me from the story with his wife. When there is an event, it's maybe but it was very difficult because the ice train, the light was there. So I was going to and the other time to go to speak up still. No, it was actually they were only blessed. Yes, I question. They didn't say what to do, right? I think it's fine, but I believe.
So no need to record anything, right?
Yeah, no more, but it's done for the day.
Yeah.
So you can just stop recording.
Yeah. So yeah, can I just
Yeah, just stop the recording. It's good.
Okay.
I mean, we're done, right? So yeah.
Yeah, I believe so. So
Okay.
let's stop the recording.
Yeah. Thank you very much. Good job.
Yeah. Okay. So, and can I just stop live streaming?